An aircraft's total drag can be defined as the sum of its parasite drag and induced drag. This lesson examines the essential aspects and significance of total drag. If the curves for parasite drag and induced drag are plotted together, you can easily see the predominance of induced drag at low speed and of parasite drag at high speed. If the two sets of values are combined, we get a curve for total drag, a shape with which you will become very familiar. Because of the way that the two component types of drag vary with speed, the speed at which total drag is at its minimum occurs where the induced and parasite drags are equal. This minimum drag speed, usually referred to as min drag speed or VMD, is an important reference for many aspects of aircraft performance. Range, endurance, glide, maneuver, landing and takeoff performance are all based on some relationship involving the aeroplane total drag curve. Since flying at VMD incurs the least total drag for flight with lift equaling weight, the aircraft will also be at the angle of attack for the maximum lift-drag ratio, LD max, which is around 4 degrees. It is important that you remember that LD max is obtained at a specific angle of attack, and also that the maximum lift-drag ratio is a measure of aerodynamic efficiency. On this subject, it is worth noting that if an aircraft is operated at the LD max angle of attack, drag will be at a minimum while generating the required lift. Any angle lower or higher than that increases the drag for a given lift force. More drag requires more thrust, which is inefficient and costly. You should also note that if IAS is varied, the lift-drag ratio will vary. Lift-drag ratio can be presented in a polar diagram, which plots CL against CD. This shows the CL increasing initially more rapidly than CD, but ultimately CD increases more quickly. LD max can be found from the drag polar by drawing a tangent to the curve from the origin, the slope of the tangent determining the value of the maximum lift-drag ratio. This is a common method of displaying the lift-drag ratio, and you will become quite familiar with it. As fuel is consumed, gross weight reduces, requiring less lift and reducing induced drag. The effect on total drag is that the curve moves down and to the left, as total drag and VMD are reduced. If the aircraft is operated at a higher weight, the curve moves up and to the right, as a result of the greater induced drag, and VMD occurs at a higher IAS. Changes in configuration, as for example on the approach to land, where landing gear, flaps, and air brakes or spoilers will be extended in a sequence appropriate to type, will create significant increases in parasite drag, but differing variations in induced drag. More lift with flaps with the increased CL, less with spoilers. The overall result is an increase in total drag, but a reduction in the min drag speed, with the curve moving up and to the left. Since transport aircraft tend to operate mostly at steady indicated airspeeds, it is relevant to consider variations of drag with IAS. At a constant IAS, dynamic pressure remains constant, so even if altitude is changed, drag will not change, even though TAS will change according to the changes in density with climb or descent. For an aircraft to be in steady flight, it must be in equilibrium. That is, with no out-of-balance forces or moments. When it is trimmed to fly at a steady speed, thrust and drag are equal. Therefore, when an aircraft is in steady flight, it can be said that the terms drag and thrust required are essentially interchangeable, so that when considering a total drag curve, it could also be looked at as a thrust required curve. For an aircraft in steady flight, if there is a change in speed without a change in power or thrust, the thrust available, there will be either an excess or a deficiency of thrust available, depending on the trim speed. We shall consider an aircraft at two speeds, at points A and B. If at speed A the speed is disturbed and rises, drag also rises, and a thrust deficiency exists. The aircraft then decelerates and settles back at its original speed. In this area of the curve, then, the aircraft is speed stable. Similarly, if the aircraft were to lose speed, drag would decrease, and the aircraft would regain the lost speed. Considering the aircraft at speed B, if it gains speed, drag decreases, and with an excess of thrust, the aircraft's speed will continue to drift up to VMD. In this area of the curve, the aircraft is speed unstable. Possibly, the most potentially hazardous situation occurs with a speed decrease in the speed unstable part of the curve, as the aircraft would then tend to decelerate further unless the deceleration is rectified with a prompt and generous application of thrust. Flight in this region of the curve is often referred to as being on the wrong side of the drag curve. Thinking back to earlier in the lesson, you will remember that lowering gear and flap and extending speed brakes lowers VMD, which has the benefit of extending the speed stable region to the left. Indeed, some aircraft fitted with air brakes routinely fly approaches with brakes out for that very reason. Finally, you will notice that the curve either side of VMD is fairly flat. In this region, the neutral IAS area, there is no distinct tendency to either speed stability or instability. However, the general rule to remember is that above VMD, the aircraft will be speed stable, and below it, speed unstable. Following on from your study of total drag, we can examine the relationship between thrust, drag, and power. You have already seen that drag in certain circumstances can also be referred to as thrust required, and you will see that a similar relationship exists with power required. They are both important airframe considerations. Although pilots tend to use the word power when discussing aircraft handling, quite often it is the case that they should be referring to thrust. Thrust is a force, a push or a pull, which opposes drag, but power is a rate of doing work. Power, then, is work over time, and work equals force times distance. So power must be force times distance over time. The force we are concerned with here is drag. Distance over time is speed, and the only true speed is the speed of the aircraft through the air, true airspeed, or TAS. We can thus rewrite the equation to read power required equals drag times TAS. If an aircraft climbs at a constant indicated airspeed, drag will remain constant, but TAS will be increasing, so power required will increase. As stated in the first part of the lesson, power is a rate of doing work, and so we must consider power required, since when the aircraft is climbing, work is being done to raise it to a higher altitude. Logically, the maximum work can be done on the aircraft in the minimum time, when the power available from the engine or engines is greatest, and the power required by the airframe is least. For easy reference, keep in mind the definition that power is a rate of doing work, and associate the words power and rate. For example, the minimum rate of descent is achieved when the aircraft is flown at the minimum power required speed, known as VMP, or min power speed. These considerations and other associated factors are covered in detail in the lessons on aircraft performance and flight mechanics. The diagrams on the screen represent data for one particular aircraft in level flight at one weight, and at sea level where IAS equals TAS. Starting with a curve for drag or thrust required against TAS. The graph for power required is constructed by multiplying each value of drag by the appropriate TAS and converting it to kilowatts. Note that the min power speed, an IAS, is lower than min drag speed. The effect of a change in altitude for an aircraft flying at min drag speed will be that its drag would not change, VMD being an IAS. However, the aircraft's TAS would be increasing, and since the power required would also be increasing in proportion, the ratio of TAS to power required is unaffected, and VMP will remain a lower speed than VMD. The information in this lesson is mainly concerned with performance, especially the relationship between minimum power speed and minimum drag speed, which is of importance when considering rates and angles of descent in a steady glide, which is covered elsewhere in the syllabus, in Chapter 12 of the OAA Principles of Flight book. A summary of the salient points from this series of lessons on drag follows in the next lesson. This final lesson in the series on drag consists of a summary of the main points. As a reminder of the divisions of drag, here is the family tree. Parasite drag is made up of skin friction drag, form or pressure drag, which together are known as profile drag, and interference drag. Parasite drag varies as the square of the IAS. If you double the speed, you get 4 times the parasite drag. If you halve the speed, you get 1/4 of the parasite drag. Designers can minimize parasite drag by streamlining, incorporating fillets and fairings, using laminar flow wing sections, and minimizing frontal area. Flight crews must ensure that the airframe, and particularly the wing, is not contaminated by ice, snow, frost, slush, insects or mud. On induced drag, you will need to remember the following key points. Spanwise airflow generates wingtip vortices. The higher the CL, or the lower the IAS, the stronger the wingtip vortices. Wingtip vortices strengthen downwash. Strengthened downwash inclines wing lift rearwards. The greater the rearward inclination of the wing lift, the greater will be the induced drag. Induced drag varies inversely as the square of the indicated airspeed. If speed is halved, the CDI will increase by 16 times, and the induced drag by 4. If speed is doubled, the induced drag coefficient will reduce to 1/16 of its previous value, and the induced drag to 1/4 of its previous value. Designers can minimize induced drag by using a high aspect ratio planform, using a tapered wing planform with wing twist or washout, and/or spanwise camber variation, and by incorporating end plates, tip tanks, winglets, or tip shaping. Total drag is the sum of parasite and induced drag. Total drag is a minimum when parasite and induced drag are equal. At low IAS, induced drag is dominant. At high IAS, parasite drag is dominant. The IAS at which the two component drags are equal is called minimum drag speed, VMD. As gross weight decreases in flight, induced drag, total drag, and VMD all decrease. At a constant IAS, altitude has no effect on total drag, but TAS will increase as density reduces with higher altitude. Configuration changes, which increase the parasite area, such as landing gear, flaps, and speed brakes, increase parasite and total drag, but reduce VMD. An aircraft flying at a steady IAS higher than VMD with a fixed power setting will have speed stability. An aircraft flying at a steady IAS at VMD or slower with a fixed power setting will usually not have speed stability. If an aircraft at a steady IAS at a fixed power setting within the non-stable IAS region encounters a disturbance which slows the aircraft, it will tend to slow further. IAS will tend to continue to decrease and the total drag to increase. The IAS for minimum power required, VMP, is slower than the minimum drag speed, VMD. Maximum TAS to power ratio, which is 1.32 VMP, occurs at VMD.
This series of lessons will teach you about the many aspects of the stall, an aerodynamic phenomenon which can result in loss of height and ultimately loss of control if not correctly recognized and handled. Such a situation would obviously be potentially very hazardous at low level on the approach or after takeoff. It is vital, therefore, that a pilot should be able to identify the signs and symptoms of stalls in any configuration or stage of flight, in order to prevent or recover from a stall with minimum height loss. You'll be taught how to do this during your flying training, but these lessons will give you the theoretical knowledge you will need to understand how and why stalls happen. Different types of aircraft exhibit different stalling characteristics, some less desirable than others, but all should give the pilot some indication of an incipient stall. Airworthiness authorities specify the minimum stall qualities that an aircraft must possess. Reference will be made in the course of the lessons to such regulations for training purposes, but you should note that these requirements are occasionally subject to change. The coefficient of lift, or CL, of an aerofoil increases with angle of attack up to a maximum CL max. Any further increase above this critical angle of attack or stalling angle will make it impossible for the airflow to follow the upper contour of the wing smoothly. The flow will separate from the surface, causing CL to decrease and drag to increase rapidly. Since the CL max of an aerofoil corresponds to the minimum steady level flight speed, the 1G stall speed, it is an important point of reference. The stall, then, is caused by airflow separation, which occurs either when the boundary layer has insufficient energy or the adverse pressure gradient becomes too great. If we look at a sequence of an approach to the stall, we can see that at low angles of attack, virtually no flow separation occurs before the trailing edge, the flow being attached over the rear part of the wing in the form of a turbulent boundary layer. As angle of attack, or alpha, is increased, the adverse pressure gradient increases, reducing the kinetic energy, and the boundary layer will begin to separate from the surface at the trailing edge. Further increase of alpha makes the separation point move further forward, and the area of the wing that is generating a pressure differential, and thus lift, becomes progressively smaller. At alphas greater than the critical angle, which will depend on the wing planform, the extremely steep adverse pressure gradient will have caused so much separation that the wing can no longer generate enough lift to support the aircraft's weight, and the wing is stalled. It is important to remember that the angle of attack is the angle between the chord line and the relative airflow. Therefore, if the angle of attack is increased up to or beyond the critical angle, an aeroplane can be stalled at any airspeed or flight attitude. If we study the lift curve shown in this sequence, it can be seen that the increase in CL is linear over a large proportion of the range of alpha up to the stall. But as the effects of separation begin to be felt, the curve begins to flatten. Eventually, CL reaches a peak and then drops at an angle steeper than the rate of increase. The alpha at which it reaches its peak is called the critical or stalling angle of attack, and the corresponding value of lift coefficient is CL max. Most aeroplanes will stall at around 14 to 16 degrees alpha. Stall characteristics vary with different kinds of aircraft, but there are common factors which may occur with all aeroplanes. For modern aircraft, during most manoeuvres, the onset of the stall is gradual. The first indications may be provided by any or all of the following. Flight controls less effective than usual. Speed low and decreasing. Nose attitude higher than normal. Light aerodynamic buffet, or the operation of a stall warning or stall prevention device. If the stall is allowed to progress beyond the incipient stage, any one of the following is symptomatic of a fully developed stall. Wing drop, nose drop, heavy aerodynamic buffet, or a loss of height. These symptoms form part of the formal stall recognition conditions described shortly. The behaviour of various types of aircraft at the stall is covered in more detail later, and recovery from the stall is described in the next part of the lesson. If a stall occurs, either incipient or fully developed, the principal action that must be taken is to reduce the angle of attack below the critical angle to decrease the adverse pressure gradient. This action may consist simply of releasing back pressure on the control column or moving it smoothly forward until the wings are unstalled. Excessive forward movement of the controls would lead to an unnecessary height loss during recovery. The use of full or maximum permitted power is usual during stall recovery to minimize height loss. As the angle of attack reduces, the airspeed will increase, and at a safe margin above the stall speed, any lost height can be regained by moving the control column back. Pilots should be careful not to pitch up too quickly, as this may restall the wing, even at a higher speed, which is known as a secondary stall and is covered in detail later in this series of lessons. The rudder should be used with great caution at any time when stalled or close to the stall, because of the possibility of causing a spin, on which more later. It is safer to use the rudder only after the wings are unstalled, and then only to prevent further yaw if a wing has dropped because it has stalled slightly before the other. It is generally safer only to use the ailerons to level the wings, also once the wings are unstalled. On swept-wing aeroplanes, the ailerons can be used to correct a wing drop, coordinated with a small amount of rudder, because design requirements for stall characteristics demand features promoting early wing root stall. However, the rudder on modern jet transports is very powerful, and excessive use can result in over-controlling, or even, in extreme cases, structural failure. At the low speeds normally associated with stalling, dynamic pressure is at a low value, and greater deflection will be required to achieve the same response as that found at a higher speed. The controls will also feel less responsive, as mentioned earlier in the lesson. If an accidental stall should occur, it is important that the recovery is effected before the process develops too far, with a large wing drop giving a high rate of descent or possibly leading to a spin. Moving a control surface alters the chord line and hence the angle of attack. An aircraft may have one wing which is less efficient than the other and stalls slightly before it, causing a wing drop. Trying to lift a dropping wing with aileron will increase its angle of attack further, taking it deeper into the stall. At the same time, the upgoing aileron on the opposite wing will decrease its angle of attack, possibly unstalling that wing, which produces more lift and exacerbates the roll already made worse by the changes in effective angle of attack. The moral of this is that ailerons should be used with great caution when close to the stall. Swept-wing aircraft basic stalling requirements, however, are designed to enable safe use of the ailerons as far as stall recognition, with small amounts of rudder, if smoothly applied, to coordinate with the ailerons. Various means of achieving this capability are discussed later. The use of rudder has already been mentioned in the earlier section on stall recovery, with its attendant risks. A coarse application of rudder before the wings are unstalled to pick up a drop wing, but inadvertently, in the wrong sense, in the direction of roll, could put the aircraft into a spin. Even if the rudder were applied to oppose a wing drop, it would require a large rudder deflection, which could well cause a spin in the opposite direction. Taken with the aforementioned restrictions on the use of the ailerons, these factors would suggest that the ailerons and rudder should be kept neutral until the wings are unstalled, and only used when the aircraft has reached a safe speed margin above the stall. A formal standard of stall recognition is established to determine when the behaviour of the aeroplane gives the pilot a clear and distinctive indication of an acceptable nature that the aeroplane is stalled. These acceptable indications of a stall, occurring either individually or in combination, are 1. A nose-down pitch that cannot be readily arrested. 2. Buffeting of a magnitude and severity that is a strong and effective deterrent to further speed reduction. And 3. The control column reaches the aft stop, that is, full up elevator, and no further increase in pitch attitude occurs when the control is held fully aft for a short time before recovery is initiated. The following section of the series of lessons deals with stall speeds and warning and prevention devices.
This section of the lesson will tell you how the stall speeds quoted in aircraft flight manuals are determined, and the parameters on which they are based. Aircraft need to fly at low speeds with high angles of attack during takeoff and landing in order to keep the required runway length to a reasonable minimum. But there must be an adequate safety margin allowed between the minimum speed for normal operations and the stalling speed. During the flight testing that takes place before type certification, prototype aircraft are stalled, and the stalling speeds established for inclusion in the flight manual. The stalling speed for small aircraft, those in the EASA category CS23, for normal, utility, aerobatic and commuter aircraft, is based on the stall speed in the landing configuration, VS0, and the speed for a given configuration, VS1. For large aircraft, in EASA category CS25, a reference stall speed, known as VSR, is used. VSR is a calibrated airspeed defined by the manufacturer, and may not be less than a 1G stall speed. It is expressed in formula form as being equal or greater than VCL max over the square root of NZW, where VCL max is the calibrated airspeed obtained when the load factor-corrected lift coefficient first reaches its maximum during the lay-down test manoeuvre. In addition, if the aircraft is fitted with a stick pusher, a stall prevention device, described in the next section of the lesson, VCL max may not be less than the speed at which the device operates. NZW is the load factor normal to the flight path when the aircraft is at VCL max. For an aircraft without a stick pusher, the speed at which it reaches its CL max at 1g, in other words its 1g stalling speed, can be considered to be its VSR. For the purpose of the test, to determine VCL max, the aircraft is flown with the following conditions: 0 thrust at the stall speed, propeller pitch, RPM controls, if applicable, at the takeoff setting, landing gear and flaps set as appropriate to the performance standard being tested, the weight to be that applicable when VSR is being used as a factor to determine compliance with the required performance standard, the centre of gravity to be in the position that results in the highest value of VSR, and the aeroplane must be trimmed for straight flight at a speed determined by the manufacturer, between 1.13 VSR and 1.3 VSR. During the test, the aeroplane must be decelerated from the trim speed at no more than 1 knot per second. An additional condition, which applies when the aircraft is fitted with a stick pusher, is that the reference stall speed may not be less than 2 knots or 2%, whichever is the greater, above the speed at which the device operates. VSR will vary with each of the conditions specified. Factors which affect VSR are thrust in excess of 0, wing contamination, and load factor. One thing that does not affect indicated stall speeds, however, is density altitude. The EASA regulations and their equivalents outside Europe specify that there must be clear and distinctive warning of a stall, sufficiently in advance of the stall for it to be avoided, both in straight and turning flight, and with the landing gear and flaps in any normal position. The warning can be provided either through the inherent aerodynamic characteristics of the aircraft itself, such as buffet, or by means of a device that will give clearly distinguishable indications under expected flight conditions. However, a visual warning that requires the attention of the flight deck crew will not suffice on its own. There must be a tactile or audible warning as well. A warning device must provide a warning in each normal configuration. Regarding the speed at which a device operates to give adequate stall warning, known as VSW, it should begin no less than 5 knots, or 5% of CAS if greater, above the speed at which stall recognition would occur, and should continue to operate until the angle of attack is reduced to about the angle at which it began. Under the same conditions, but also in straight flight, at idling power, and with the C of G which gives the maximum VSR, there should be a minimum of 3 knots or 3% of CAS above VSR. The regulations also stipulate that the warning margin must be sufficient to allow the pilot to prevent a stall if recovery is initiated 1 second or more after the warning in a 1.5 G turn, decelerating at 2 knots per second, with gear and flaps in any normal position, and with power and trim set for straight flight at 1.3 VSR. Finally, stall warning must also be provided in each abnormal flap or slack configuration likely to be used in flight following system failures, including all configurations covered by flight manual procedures. It is possible that adequate stall warning will be provided by the airflow separating fairly early and causing buffet over the wing and tail plane, but this is often insufficient, and so a device which simulates or substitutes for aerodynamic buffet is usually fitted. Artificial stall warning on small aircraft is usually given by a buzzer or horn, but on modern large aircraft a stick shaker is used in conjunction with lights and a noisemaker. The stick shaker is intended to represent the aircraft's natural buffet by replacing it with a tactile warning. The noisemaker is added in parallel to ensure that the warning is noticed if the pilot's hands are not on the controls. For example, if the autopilot is engaged. The device consists of a pair of electric motors, one on each control column and rotating an eccentric weight to generate vibration. Artificial stall warning devices can receive their signals from a variety of detectors, all of which are activated by changes in angle of attack. The leading edge stall warning vane, or flapper switch, usually used on small and medium-sized aircraft, is positioned so that at normal angles of attack, the airflow holds it down. But as angle of attack increases, the stagnation point moves down and back around the leading edge, and the change in pressure raises the switch, making the contact. The alpha vane is mounted on the side of the fuselage and trails in the relative airflow. The fuselage effectively rotates around it, and the vane thus senses the angle of attack. The stick shaker is activated at the appropriate alpha value. Another fuselage-mounted device is the angle of attack probe, consisting of a lateral tube with slots or holes sensitive to changes in the relative airflow, which generates the necessary signals as alpha increases. All of these devices sense angle of attack, and therefore automatically take care of changes in aircraft mass. The alpha vane and probe can also compute the rate of change of alpha and give earlier warning in the case of faster rates of approach to the stall. The detectors are usually datum compensated for configuration changes, and are always heated or equipped with an anti-icing facility. There are normally sensors on both sides of the fuselage to allow for any asymmetric airflow due to side slip. This section of the lessons on stalling deals with the characteristics of various wing forms and how they affect an aircraft's behaviour at the stall. We shall start with a summary of the requirements for stall characteristics, laid down by the European Aviation Safety Agency, EASA, and the American Federal Aviation Regulations, or FAR. The rules specify, first, that it must be possible to produce and to correct roll and yaw by unreversed use of aileron and rudder controls up to the time the aeroplane is stalled, and that no abnormal nose-up pitching may occur. The longitudinal control force from the elevators must be positive up to and throughout the stall. In addition, it must be possible to promptly prevent stalling and to recover from a stall by normal use of the controls. For stalls with wings level, the roll occurring between the stall and the completion of the recovery may not exceed approximately 20 degrees. The rules for a stall in the turn are a bit more complex, as a wing drop or roll at the stall is potentially more likely. The action of the aeroplane after the stall may not be so violent or extreme as to make it difficult, with normal piloting skill, to effect a prompt recovery and regain control of the aeroplane. The maximum bank angle that occurs during recovery may not exceed approximately 60 degrees in the original direction of the turn, or 30 degrees in the opposite direction for deceleration rates up to 1 knot per second. If the deceleration is more than 1 knot per second, these bank angles are increased to 90 and 60 respectively. You have learned that stalling is due to airflow separation, resulting in a loss of lift and an increase in drag that will cause the aircraft to lose height. This is generally true, but there are some aspects of aircraft behaviour and handling at or near the stall which depend significantly on the wing's aerofoil section and plan form. The shape of an aerofoil section will influence the manner in which it stalls. Some sections will stall very suddenly, with a marked drop in lift, whilst others have a more gradual approach to the stall, with a less dramatic loss of lift. In general, an aeroplane should not stall too suddenly, and the pilot should have adequate warning of the approach of the stall by means of natural warnings, such as airframe buffet or decreasing control effectiveness. If, however, a particular wing design is likely to stall too abruptly, it will be necessary to provide some sort of artificial pre-stall warning, or even a stall prevention device. There are several features of an aerofoil section design that affect behavior near the stall. First, the radius of the leading edge. A large radius will give a much more gradual stall than a sharper, small radius leading edge. Likewise, a thick section, greater camber, particularly near the leading edge, and a forward point of maximum thickness and camber are all more conducive to a gradual, more gentle stall than the opposite characteristics. These features are more typical of a wing designed for efficient high-speed operation. With a sharper leading edge, a low thickness chord ratio, and an aft maximum thickness and camber, a comparison of the shapes of the two lift curves shows the difference between the profile's stalling characteristics. As well as the wing's aerofoil section, its shape or planform will also have an effect on how it stalls. On basic, conventional wing planforms, the separation that causes the stall will not occur simultaneously at all points across the wing. On a rectangular wing, separation tends to start at the wing root trailing edge and spread forward and out towards the tip. Since the reduction in lift occurs initially inboard near the C of G, even if it happens on one wing slightly before the other, there is little tendency for the aircraft to roll. The aircraft loses height, but remains more or less wings level. As the aircraft stalls, the centre of pressure moves aft, causing the nose to drop, thus reducing the angle of attack. This gives the aircraft a natural tendency towards a recovery from the stall. The separated airflow from the wing root passes over the fuselage and tail unit, and the aerodynamic buffet caused by it can provide a warning of the approaching stall. The ailerons, being located outside the separated flow, will tend to remain effective as the stalling sequence starts. All these factors give the most desirable kind of response to a stall, namely aileron effectiveness, nose drop, aerodynamic buffet, and absence of violent wing drop. Despite these advantages, for large jet transport aircraft, a rectangular wing planform would impose unacceptable bending moments and would be less efficient at higher speeds. Compared to a rectangular wing, a tapered wing creates lower bending moments for a given span and is more efficient. The airflow separation on a tapered wing happens first in the area of the wingtips, reducing lift on the outboard part of the wing. This is because the weak wingtip vortices allow separation earlier than the inboard part of the wing, where the stronger vortices from the wider chord reduce the effective angle of attack. If an actual basic tapered wing were allowed to stall in this way, the stall would create aileron buffet and perhaps a violent wing drop, which greatly increases the likelihood of entering a spin. In addition, there would be no buffet at the tailplane, no strong nose-down pitching moment, and very little, if any, aileron effectiveness. To counter these undesirable characteristics, a tapered wing must be modified using one or more of the aerodynamic features described next. The wing can be designed with a twist, which reduces the angle of incidence, the angle between the mean chord line and the fuselage datum line, towards the tip. This is known as washout, and decreases the angle of attack at the tip relative to the root, and the root will tend to stall first. Another method is to vary the aerofoil section across the span, so that the sections near the tip have greater thickness, greater camber, or both. The higher CL max of such sections delays the stall at the tips. Leading edge slots at the wingtips re-energize the boundary layer by increasing its kinetic energy. The result is an increased CL max, delaying separation at the tips and retaining aileron effectiveness. The function of slats and slots is fully described in the lesson on high lift devices. The stall pattern can be influenced by forcing it to start from the root. This could be managed by designing the wing with a smaller leading edge radius at the root, but this is less efficient overall. The desired result can be achieved by fitting small wedge-shaped strips, stall strips, to the leading edge, which promote separation at high angles of attack, but will not affect the efficiency of the wing at cruising speed. Vortex generators, another device that can re-energize the boundary layer, consist of rows of small thin blades about 2.5 centimeters high, set at a small angle, and projecting vertically into the airstream to produce vortices over the upper wing surface. They each generate a small vortex, which causes the free stream flow of high-energy air to mix with and add kinetic energy to the boundary layer, delaying separation. A swept wing will allow higher maximum speed, but has a greater tendency than a straight wing to stall first near the tips. This loss of lift at the tips moves the centre of pressure forward and inward, giving a destabilizing nose-up pitching moment. The lift is now concentrated inboard, and the maximum downwash impinges on the tailplane, adding to the nose-up moment. As soon as a swept wing begins to stall, both the forward CP movement and the increased downwash at the tailplane causes the nose to rise rapidly, further increasing the angle of attack. This is obviously undesirable and unacceptable behaviour at the stall, and can result in a complete loss of control in pitch from which it may be very difficult, if not impossible, to recover. This phenomenon is known as pitch up, and is a very dangerous characteristic of some high-speed swept-wing aircraft. The tendency of a swept back wing to tip stall is due to the induced spanwise flow of the boundary layer from root to tip, and there are several design features that can be incorporated to address this effect, to give more acceptable stall properties. Wing fences are thin, upright metal strips, which generally extend from leading to trailing edge and restrict the outward drift of the boundary layer. Vortilons are similar to wing fences, but are shorter and mounted under the wing leading edge. The support pylons of pod-mounted engines act in the same way, which is to create a small but intense vortex over the wing's upper surface at high angles of attack to form an aerodynamic wing fence. Finally, there is a feature rarely used on modern high-speed jet transports, but which did appear on earlier generation jets, such as the Comet airliner and the Hunter. The sawtooth leading edge, like the vortilon and pylon, also produces a vortex at high angles of attack to act as a wing fence. As you have learned in the previous part of this series of lessons on stalling, an unmodified swept wing will stall first near the tips. And since the tips are well aft of the centre of gravity, the loss of lift causes the nose to rise rapidly and further increase the angle of attack. This phenomenon of pitch up stalls more of the wing. Drag will increase rapidly, lift will reduce, and the aircraft will start to sink at a constant nose-high pitch attitude. This results in a rapid additional increase in angle of attack. Separated airflow from the stalled wing will immerse a high-set tailplane, or T-tail, in low-energy turbulent air, and elevator authority is greatly reduced, making it impossible for the pilot to reduce the angle of attack. The aircraft will become stabilized in what is known as the superstall, or deep stall. The two principal factors involved in the superstall are a swept-back wing and a high-mounted tailplane. But of the two, by far the more significant is the swept wing, with its tendency to stall at the tips, causing the pitch-up phenomenon. Aircraft such as the MD-80, Boeing 727, Fokker 28, and the BAC 111, the aircraft on which the phenomenon was discovered during its flight testing in 1963, all have swept wings and T-tails. They also have rear fuselage-mounted engines, which are the reason for the T-tail. But apart from the possibility of the engines causing some turbulence and blanking of the airflow once the aircraft is already stalled, they do not in themselves contribute to the stall. Several devices and design features that can delay the tip stall by various means were described in the last lesson. Methods of reducing the spanwise movement of the boundary layer include wing fences, vortilons, engine pylons, and sawtooth leading edges. Vortex generators are a frequently used design feature that not only delay tip stall, but also improve stalling characteristics by maintaining aileron effectiveness down to lower speeds. The wing root can be made to stall before the tips by changing the aerofoil section at the root, by fitting stall strips, or by fitting Kruger flaps on the inboard sections of the wing, alongside the more efficient variable camber leading edge flaps. Both of these types of flap are described in the lessons on high lift devices. An aircraft which exhibits, or is likely to exhibit, superstall characteristics must be fitted with a device that will prevent it from ever stalling. The device is the stick pusher, developed after the loss of the 111 previously mentioned. Once a superstall commences, its progression is too fast for human response, and the aircraft cannot be unstalled. The stick pusher is incorporated in the elevator control system, and, as its name implies, physically pushes the control column forward at a certain angle of attack before the critical angle, and reduces the angle before a stall can occur. The push force is typically about 80 pounds, which is regarded as being high enough to be effective, but not too high to hold in the event of a runaway. A cutout is included to dump the system in the event of a malfunction. But, once dumped, the system can't normally be reset in flight. In normal operation, once the stick pusher has operated, it will disengage automatically as the angle of attack reduces below a preset value. In an earlier lesson, you learned about the reference stall speed, VSR, the calibrated airspeed at which a large aircraft in the EASA category CS-25 stalls. You also learned that stalling is caused by exceeding the critical angle of attack. Stalling has nothing to do with the speed of the aircraft. The critical angle of attack can be exceeded at any speed. It is worth noting here that to do so in the upper end of an aircraft's speed range is likely to exceed its structural limitation, or G limit. However, it has been shown that if an aircraft is flown straight and level, and the speed reduced at a rate of not more than 1 knot per second, then it is possible to identify the CAS at which it stalls, which will be a 1g stalling speed. This reference stall speed is the speed on which are based the recommended takeoff, maneuver, approach and landing speeds, which will give an adequate safety margin above the stall during normal operations. These are calculated as proportions of VSR: 1.05, 1.1, 1.2, 1.3 VSR, etc. There are several factors that can affect the value of VSR. They are weight, maneuvering the aircraft, increasing the load factor, configuration changes, affecting maximum lift coefficient and pitching moment, engine thrust or propeller slipstream, Mach number, wing contamination, and heavy rain. We shall now examine how these changes work. In straight and level flight, the weight of the aircraft is balanced by the lift. So the load factor, which is lift over weight, is 1. Whilst n in brackets is the correct symbol for load factor, the relationship between lift and weight has for years been popularly known as G. 1G corresponds to the force normally acting on us, that is, gravity. If more lift is generated than weight, the load factor will be greater than 1. The force acting on the aircraft and everything in it, including of course the pilot, will be more than normal gravity. If lift equals weight, the load factor will be 1, as you have seen. And from the lift formula, lift equals half rho v squared times CL times S, it can be seen that lift will change whenever any of the other factors in the formula change. Taking density, rho, and wing area, S, to be constant for this example, consider what would happen if thrust is reduced. The speed, v, would reduce because of drag. And from the formula, you can see that lift would decrease. So, to keep lift constant and maintain 1G flight at a reduced speed, CL must be increased by flying at a higher angle of attack. Any further reduction in speed would need a further rise in angle of attack, with each succeeding lower CAS corresponding to a greater angle of attack. Eventually, at a certain CAS, the wing reaches its critical angle and CL max, beyond which any further rise in angle of attack will precipitate a stall. We can transpose and adapt the lift formula to give us a formula for a 1G stalling speed, which equals the square root of lift over half rho times CL max times S. Note that density altitude does not affect indicated stall speed. At CL max for 1G flight, a change in weight requires a change in lift, and it can be seen from the 1G stall speed formula that, for instance, an increase in weight, and therefore lift, will increase Vs 1G. The relationship between basic stalling speeds at two different weights can be obtained from the following formula. The new speed equals the old speed multiplied by the square root of the new weight as a proportion of the old weight, or the square root of new over old. The angle of attack at which the stall occurs will not be affected by the weight. This is provided that the appropriate value of CL max is not affected by speed, which will only happen at speeds above Mach 0.4. To maintain a given angle of attack, say critical angle or alpha CL max, in level flight if the weight and therefore the lift required is changed, it is necessary to change the dynamic pressure. In other words, the CAS. For example, if an aircraft stalls at 150 knots at a weight of 588,600 newtons, what is the 1g stalling speed at 470,880 newtons? Using the formula, the new to old weight proportion is 470,880 over 588,600, which is 0.8. The square root of this is 0.894, which multiplied by 150 is 134. So the new stalling speed is 134 knots. A useful rule of thumb that can be derived from such calculations is that halving the percentage change in weight, either up or down, will give the approximate percentage change in stalling speed. In the example, a 20% weight reduction gives about a 10% speed reduction. This rule of thumb can be very useful, not least as a gross error check during exams. As you know, in straight and level flight, lift balances weight. But in a level turn, for example at 45 degrees, as shown here, the weight will still be acting vertically downwards, and the wings need to produce a vertical lift vector to balance it. However, as you can see from the diagram, the lift vector is tilted at 45 degrees, and if it is resolved into vertical and horizontal vectors, it is insufficient to balance the weight. The lift must therefore be increased, so that its vertical component balances the weight, and the relationship between the vertical force and the lift required can be found using trigonometry, using the symbol phi as the bank angle and taking the vertical force required as 1, the adjacent, lift being the hypotenuse. Cosine equals adjacent over hypotenuse, and if we transpose this formula, we arrive at L equals 1 over cos phi. Cos phi in this case, at 45 degrees, is 0.707. 1 divided by 0.707 is 1.41. So, for a level 45-degree bank turn, the lift must be 1.41 times that of straight flight, or, to put it another way, increased by 41%. You learned in the previous part of this lesson on stalling that to bank an aircraft and maintain level flight, lift must be greater than weight. The additional lift required is gained by increasing the angle of attack. The measure of the relationship between lift and weight is known as the load factor. Increasing lift in a turn increases the load factor. So as bank angle increases, load factor increases. In straight and level flight at CL max, it would be impossible to turn and maintain altitude, as trying to increase lift would stall the aircraft. If a turn were to be started at a speed above the stalling speed, then at a certain angle of bank, CL would reach its maximum, and the aircraft would stall at a speed higher than the 1g stalling speed. The increase of lift in a level turn is a function of the bank angle. Using the following formula, it is possible to calculate stalling speed as a function of bank angle or load factor. The turning stall speed will equal the 1g stall speed multiplied by the square root of 1 over the cosine of the bank angle. As an example, if the 1G stalling speed is 150 knots, what would be the stalling speed at 45 degrees of bank? The working on the screen shows the result to be 178 knots CAS. Using the same sequence for 60 degrees of bank, a 2G turn in level flight gives a stalling speed of 212 knots CAS, which is 41% greater than the 1G stalling speed. The 45-degree stalling speed is 19% higher, and since these figures are ratios, they will hold good for any aircraft. As bank angle is increased, the stalling speed will rise exponentially. Whilst operating at high CLs, particularly during takeoff and landing, only moderate angles of bank should be used when manoeuvring the aircraft. For modern high-speed jet transports, the maximum bank that should be used is 30 degrees, except in an emergency. The normal maximum under instrument flight rules, IFR, is 25 degrees, or the angle of bank for a rate 1 turn, 3 degrees per second, if this is less. At higher altitudes, the normal maximum would be about 10 to 15 degrees. In brief, load factor does not affect the stalling angle of attack, but the stalling speed increases in proportion with the square root of the load factor, in the same way as it does with the weight increase, since G is an effective increase in weight. Modern high-speed jet transport aircraft have swept wings with relatively low thickness chord ratios. For example, the Airbus A310 has a ratio of 12%. The overall value of CLmax for these wings is fairly low, and the clean stalling speed therefore correspondingly high. To reduce the takeoff and landing speeds and distances, various high-lift devices are used, increasing the value of CLmax. In addition to lowering the stalling speed, these devices, which principally comprise leading edge flaps and slats and trailing edge flaps, will usually alter the stall characteristics. From the 1G stall formula, it can be seen that an increase in CLmax will reduce the stalling speed. It is possible, with modern high-lift devices, to increase the CLmax by up to 100%. High-lift devices, which are fully described in the next set of lessons, decrease stall speeds and so minimum flight speed, enabling shorter takeoff and landing runs. This is their primary, and for airliners, their sole purpose. The EASA regulation 25.103b states that VCL max is to be determined with the CG position that results in the highest value of reference stall speed. If the CG is in front of the centre of pressure, the CP, giving a nose-down pitching moment, as is usual, the tail plane must provide a download to maintain equilibrium, but the wing must produce more lift to balance the increased force of weight plus tail downforce. If the CG is further forward, it will produce a greater pitching moment, which must be balanced by a greater downforce from the tail plane. This in turn requires more lift to counter the downforce. From the 1G stall formula, you can see that greater lift gives a higher stalling speed, with the conclusion that forward movement of the CG increases the stalling speed. With landing gear up, the thrust-drag couple is not great, but when the gear is lowered, the profile drag below the CG is increased, which gives a nose-down pitching moment. This must be balanced by increasing the downforce of the tailplane, which in turn needs more lift to balance it. Any change of CG caused by a change in longitudinal position of the gear as it extends will have very little effect. The change in profile drag is far more significant, and the conclusion is that lowering the landing gear increases stall speed. Regarding engine thrust, the EASA Regulation 25.103b states that VCL max is to be determined with zero thrust at stall speed, and it is assumed that the aircraft is supported entirely by lift. If thrust is applied close to the stall, the nose high attitude will produce a vertical component of thrust, which helps to support the weight, and less lift is required. Propellers will create an extra effect because of the slipstream. The most important factors in this situation are engine type, propeller or jet, thrust to weight ratio, and the inclination of the thrust vector at CL max. With propeller-driven aircraft, the slipstream velocity behind the propellers is greater than the free stream flow, depending on the thrust. Thus, at low IAS and high power, the dynamic pressure within the slipstream is higher than that outside it, and generates more lift than at zero thrust. The lift at any given IAS or angle of attack will be significantly affected. For instance, if the aircraft is in the landing flare and power is reduced suddenly, the resulting loss of lift could cause a heavy landing. On the other hand, a potentially heavy landing can be prevented with a judicious burst of power. A typical jet aircraft does not experience the induced flow velocities of prop-driven aircraft, the only significant factor being the vertical component of thrust. This means that, since less lift is required to support the aircraft, there is lift in hand to decelerate to a lower speed. The effect on stall speed at high thrust can be large, but since there is no induced flow, the angle of attack at the stall will be very similar to that of a power-off stall. The conclusion for both categories of aircraft is that power on stall speed is less than power off. As an aircraft flies faster, the streamline pattern around the wings begins to change. Above about Mach 0.4, 4/10 of the speed of sound, the phenomenon of compressibility becomes significant. Mach 0.4 equates to around 300 miles per hour. Pressure waves generated by the wing's passage through the air propagate ahead of it at the speed of sound, and cause the air ahead of the wing to curve upward, or upwash, towards the low-pressure upper surface. At low speeds, the streamline pattern is affected well ahead of the wing, and the air has a fair distance in which to upwash. As speed increases, the wing gets closer to its leading pressure wave, and the air has less space in which to upwash, and so approaches the wing more steeply. The change in streamline pattern accentuates the adverse pressure gradient near the leading edge, and flow separation occurs at a lower angle of attack. Above Mach 0.4, CL max decreases, as shown in the diagram on screen. According to the 1G stall formula, a drop in CL max will increase the stalling speed. At a constant EAS, TAS will increase. Also, outside air temperature, or OAT, drops with increasing altitude, causing the local speed of sound to decrease. Mach number is proportional to TAS and inversely proportional to the local speed of sound, or A. As an equation, M equals TAS over A. At a constant EAS, Mach number will increase with altitude. The graph, now on the screen, shows the variation of stalling speed with altitude at a constant load factor. This type of curve is called the stalling boundary for the given load factor, in which altitude is plotted against EAS. At the load factor shown, 1g, the aircraft cannot fly to the left of this boundary. You can see that at lower altitudes, stall speed does not vary. This is because the Mach number at the stall is less than 0.4, too low for compressibility to have any effect. By about 30,000 feet, the Mach number has risen to the extent that compressibility is significant and the rise in stalling speed is apparent. The conclusion here, then, is that stall speed will initially stay constant with altitude, but will increase with compressibility above about Mach 0.4. The various factors affecting stalling speed considered so far have been pretty much known quantities, explored during flight testing and promulgated in aircraft manuals. But contamination on the wing, particularly ice, frost or snow, can drastically affect the wing profile and affect the nature of the boundary layer, giving unknown and untested stalling speeds and characteristics. Let's consider the effects of these three main types of contamination, starting with ice. Ice formation on the wing will produce large changes in wing contour, particularly on the leading edge, leading to severe local adverse pressure gradients. High surface friction will considerably reduce boundary layer kinetic energy. These hazards cause a large drop in CL max and can increase the stall speed by up to 30% without any change in angle of attack. The extra weight of the ice will also increase the stalling speed, but the reduction of CL max is by far the greater effect. The effect of frost is more subtle. An accumulation of a hard layer of frost on the wing upper surface gives a texture of considerable roughness. Tests have shown that leading edge and upper surface contamination, with a thickness and roughness comparable to coarse sandpaper, can reduce lift by as much as 30%, increase stalling speed by 10 to 15%, and increase drag by 40%. Whilst the basic shape and aerodynamic contour of the wing are unchanged, the increase in skin friction reduces the kinetic energy of the boundary layer, and separation will occur at a smaller angle of attack and at lower CLs than a clean wing. The effect of snow can be similar to frost in that it will increase surface roughness. In addition, any deposit more than a light dusting can add significant weight and alter the aerodynamic profile. If there is any snow on the aircraft, it must be removed before flight. The idea that snow will blow off the wings during taxi or takeoff is a complete misconception, as has been tragically proved on occasions. Notably, the crash of a Boeing 737 into the Potomac River, Washington, in January 1982, which killed 78 people, and in which snow on the wings and tailplane was one of several contributory factors. The pilot in command is legally required to ensure that his aeroplane is aerodynamically clean at takeoff. It is vitally important that the time limitations, the holdover time, on any de-icing or anti-icing process are adhered to. If this time is exceeded before takeoff, the aircraft must be de-iced again. Guidance is available to pilots in the CAA's Aeronautical Information Circular number 106 of 2004, Pink 74, issued 11th of November 2004, entitled Frost, Snow and Ice on Aircraft. AICs are reissued from time to time, so you should check for updates. To summarize the effects of contamination, we can say that while the reduction in CL max with frost is not usually as much as with ice formation, its effect is probably more than may be expected from the comparatively smaller change in profile. The effect on the boundary layer's kinetic energy is a major factor influencing the separation of the airflow. The increase in stalling speed due to ice formation is difficult to quantify, as accretion rates and patterns and ice types vary greatly. Frost is a significant hazard, but will not form on upper surfaces in flight, although it does form under fuel tanks in a descent from a sub-zero high level into warmer, moist air, but this is usually of short duration. Snow, particularly wet snow, at temperatures not far below zero, presents a very serious hazard. All will affect stalling speed. The moral is that any contamination is too much, and none must be allowed to remain on any surface before flight. De-icing is essential. As mentioned earlier, there have been cases involving loss of control in icing conditions due to unexpected stalling at speeds considerably higher than the normal stalling speeds, possibly accompanied by sudden rolling. Control can be lost as a result of a contamination-induced stall, the onset of which can be so insidious as to be difficult to detect until it is too late. The following advice may help you to recognize and avoid these gradual stalls, or recover from one if it does occur. First, a loss of performance in icing conditions may indicate a serious ice buildup, possibly unseen, which is causing a gradual loss of lift and increase in drag. Such a buildup can cause the aircraft to stall at about 30% above normal stall speeds. The longitudinal characteristics of an icing-induced stall may be so unobtrusive that the pilot is unaware that it has occurred. A stall warning system, normally triggered by angle of attack, may not be activated by a low alpha stall, but Buffet may assist in stall recognition. The first clue may be a roll control problem, manifested either as a divergent roll oscillation or a wing drop. A combination of roll oscillation and onset of high drag can cause the aeroplane to enter a high rate of descent unless prompt recovery action is taken. If a roll control problem develops in icing conditions, the pilot should suspect an icing-induced stall and take immediate recovery action. The anti-icing system, if fitted, should have been on prior to entering icing conditions, in accordance with operating procedures. If not, it must be activated immediately, and consideration given to leaving icing conditions by track or level adjustment. The tailplane is an aerofoil, and because it is thinner than the wing, will tend to accumulate ice sooner and more quickly than the wing, but with similar effects. However, the tailplane, often an inverted aerofoil, usually produces a downforce. So if it stalls, the loss of downforce will cause a pitch down, with at least a temporary loss of control. Stalling of an ice-contaminated tailplane could be precipitated by the lowering of the flaps, which increases the downwash over the tailplane and consequently alters its effective angle of attack and takes it beyond the critical angle in a negative sense. It should be borne in mind that the tailplane will usually be producing downforce, which is lost if the tailplane stalls. In the event of a sudden pitch down when lowering flaps, the initial recovery action is to retract the flaps, reducing the downwash. Heavy rain, whilst not as hazardous as its freezing cousins, ice, frost and snow, can also have a detrimental effect on stalling speeds and drag. The rain will form a film on the aircraft's surface, increasing the weight, and therefore the stalling speed slightly. As the film of water runs back over the wing, it will distort the profile, roughen the surface, and distort the airflow over the whole aircraft. CL max will decrease, increasing the stalling speed. The surface film will increase interference, profile, and form drag. The approximate overall increments are: for light rain, 5%, moderate rain, 20%, and for heavy rain, up to 30%. This extra drag increases the thrust required. A further consideration, which does not in itself affect stalling speed, is the impact of heavy rain. Lost momentum will require more thrust to maintain speed, and the rainfall will tend to push the aircraft downwards, in much the same way as microburst wind shear, with which it may well be associated. With the conventional layout of the rear-mounted tailplane, the wing stalls first, and longitudinal stability and control are maintained. On the tail-first canard layout, if the wing, the main plane, stalls before the foreplane, then stability will be lost. But if the foreplane stalls first, then control will be lost, and the maximum value of CL is reduced, since both foreplane and main plane are lifting surfaces. In the next lesson in this series on stalling, we return to conventional aircraft and the topic of spinning. When an aircraft is stalled, either inadvertently or deliberately, the motion of the aircraft may, in certain circumstances, develop into a spin. The important general characteristics of a spin are as follows. The aircraft is descending in a steep helical path about a vertical spin axis. The angle of attack of both wings is well above the critical angle. The aircraft has a high rate of rotation around the spin axis. It will also have a high rate of descent. The speed will be low, but possibly slightly above the basic stalling speed, and may be oscillatory. If the speed is relatively high, and possibly also increasing, the aircraft is not in a spin, but a spiral descent or spiral dive. Viewed from above, the aircraft executes a circular path about the spin axis, and the radius of the helix is usually less than half a wingspan. The aircraft may be spinning either erect or inverted, although inadvertent inverted spins are rare, as a fair amount of negative G is involved. The aircraft will be rolling, yawing, and pitching simultaneously. The spin is one of the most complex of all flight maneuvers. It can be defined as an aggravated stall resulting in auto-rotation, meaning that the rotation, which can start without the use of the appropriate controls, for example, a roll or wing drop without aileron movement, is self-sustaining aerodynamically, and will continue until action is taken to correct it. During the spin, the wings are unequally stalled. A spin cannot occur unless the wings are stalled, but is most likely to happen when one wing stalls before the other. That wing will drop, and the aircraft will yaw in the direction of the lower wing. The change in effective relative airflow from the roll deepens the stall on the downgoing wing and lessens it on the upgoing wing. The cause of an inadvertent spin is exceeding the critical angle of attack with an inappropriate use of rudder. In other words, flying out of balance. If prompt recovery action is not taken, an incipient spin may well develop into a full spin. Coordinated use of the flying controls is always important, but especially so during flight at low speed and high angles of attack. Although most pilots are able to maintain coordinated flight during routine maneuvers, this ability is often degraded when attention is divided by distraction from the primary task of flying the aeroplane. Distraction could be caused by even a minor technical problem within the aircraft, concentration on external events or features, obstacle clearance, or the proximity of another aircraft. A spin may also develop if forces on the aircraft are unbalanced in other ways. For example, yaw forces following engine failure in a multi-engine aircraft, or a lateral imbalance due to uneven fuel usage. There are 3 phases or stages of a spin. The first is the incipient spin. Incipient from the Latin for start or begin, and exists from the time the aeroplane stalls and autorotation starts until the spin is fully developed. This phase can be regarded as up to the end of the first full turn. A full or fully developed spin exists from the time the angular rotation rates, airspeed and rate of descent are stabilized from one turn to the next. The third phase, the spin recovery, starts when the anti-spin forces overcome the pro-spin forces. As already mentioned, if at the critical angle more lift is lost from one wing than from the other, it will drop. The relative airflow will now be inclined upwards, increasing its effective angle of attack. As the aircraft rolls, the upgoing wing has a reduced angle of attack and remains less stalled than the other wing. The asymmetry of lift increases as the aircraft yaws towards the low wing, accelerating the outside wing and decelerating the inside one. The aircraft is now said to be in the self-sustaining state of autorotation. As with any stall, the nose will drop, and as inertial forces take effect, the spin usually stabilizes at a steady rate of rotation and descent. It is vitally important that recovery from an unintentional spin is initiated as soon as the spin is recognized, since many aeroplanes will not easily recover from a full spin, taking several turns before recovery action takes effect. Recovery from an incipient spin is simpler, quicker, and will incur a much smaller height loss than a full spin recovery. It usually involves centering all controls promptly, then regaining straight and level flight when rotation stops. Every aeroplane type has its own spin characteristics, and any individual aeroplane spin behavior will depend on loading, power, configuration, and other factors. Both the total mass of an aeroplane and the distribution of that mass will influence spin characteristics. Greater mass generally means slower initial spin rates, but these may increase if the spin is allowed to progress. The higher angular momentum will extend the time and height necessary for recovery in a heavy or heavily loaded aeroplane. Within the loading of the aircraft, the centre of gravity is more significant than the mass itself, as it affects the aircraft's resistance to spinning, as well as its behaviour in the spin. A CG near the forward limit makes the aircraft more stable, with higher control forces, which make it less likely for the pilot to make large, abrupt control movements. The aircraft will be easier to trim, but its stalling speed will be higher than with a neutral or aft CG. A CG towards the aft limit decreases longitudinal static stability and reduces pitch control forces, which tends to make the aircraft easier to stall. If a spin is entered with an aft CG, the spin attitude will be flatter than with a neutral or forward CG. If the CG is at or outside the aft limit, if power is left on, or even if, in some aircraft types, the recovery actions are incorrect or incomplete, the spin may become flat. A flat spin is characterized by a near-level pitch and roll attitude, with the spin axis close to the CG. Although the height lost in each turn of the spin may thus be less than in a normal spin, the very high yaw rate, often more than 1 turn per second, results in a high rate of descent. The relative airflow in a flat spin is nearly straight up, keeping the wings at very high angles of attack. But, more importantly, the upward flow over the tail unit may render the elevator and rudder ineffective, making recovery impossible. Recovery from a stall is achieved by reducing the angle of attack to restore smooth airflow over the wings. A spin recovery has the extra element of needing to stop the rotation. The very complex aerodynamics of a spin may dictate significantly different recovery procedures for different aircraft types. So there can be no universal spin recovery procedure for all aeroplanes, but there will be elements common to most. The recommended recovery for some types involves simply reducing power to idle and centralizing all flying controls or relaxing any pressure applied to them. At the other extreme, some designs dictate that a precise set or sequence of control movements is carried out, timed to coincide with certain points in the rotation and for several turns. That said, there is a general recovery procedure which would be effective for most conventional aircraft in an erect spin, although the manufacturer's procedures, published in a specific type's flight manual, should always be followed. First, move the throttle or throttles to idle. This minimizes height loss and reduces the likelihood of a flat spin developing. It also eliminates asymmetric thrust in multi-engine aircraft and reduces engine torque and propeller gyroscopic effects which could aggravate the spin. Secondly, although this action can be done simultaneously with the first, set the ailerons to neutral. Aileron deflection can contribute to abnormal spin characteristics. Apply full rudder to oppose the spin to stop the yaw. The direction of spin is best determined from the turn needle or coordinator. The slip ball should not be used, as it is not a reliable indicator of yaw direction, possibly being affected by its position in the cockpit. Once full rudder has been applied and held, the control column should be steadily moved forward until rotation ceases. The forward movement should not be commenced simultaneously with the rudder, in order to allow the anti-yaw force of the rudder to take effect with minimum blanking from the elevator's downward movement. As soon as rotation stops, centralize all controls, particularly the rudder, as if full rudder to oppose the spin is held, the aircraft may enter a spin in the other direction. With some aircraft, the spin may speed up slightly before stopping. Recover from the ensuing dive with back pressure that increases progressively with speed, remembering that too slow a pull-out could result in excess height loss or exceeding aircraft speed limitations, or both, and too abrupt a recovery could result in a further stall at a higher speed. Reset the power as necessary to resume normal flight, taking care to stay in limits. There are some circumstances under which stalls can occur without the normal warning signs and with possibly unexpected or different symptoms from a straightforward simple stall. A crossed control stall can occur when flying at high angles of attack with rudder applied in the opposite sense to the ailerons, over-applied, or even just applied when not required. In other words, in any out-of-balance state. This state will be confirmed by the displacement of the ball in the slip indicator. Crossed control stalls can occur with little or no warning. One wing will stall well before the other, and a quite sudden wing drop can occur. The instinctive reaction to correct the wing drop with aileron must be resisted, as it could make the asymmetry of lift worse. At all times, and especially at low airspeeds in combination with high angles of attack, the rudder should be used to keep the ball in the middle to maintain balanced, coordinated flight. An accelerated stall is caused by an abrupt or excessive pitching up demand on the flying controls. It can occur during a sudden change in flight path, during maneuvers demanding high pitch rates, such as steep turns or recovery from a dive. It is called an accelerated stall, or G-stall, because it occurs at a load factor greater than 1G. An accelerated stall is usually more sudden than a 1G stall, the first sign usually being heavy airframe buffet, and may be unexpected because of the relatively high airspeed. For example, in a 2G turn, stalling speed will be 1.41 times the 1G speed, and in a 4G dive pull-out, double the 1G speed, the increase being, as you have learned, proportional to the square root of the load factor. The so-called secondary stall is actually no different aerodynamically from an accelerated or G-stall, being a stall at a load factor greater than 1. It is known as a secondary stall when it is triggered while attempting to recover from a stall, usually by trying to hasten the recovery. This can happen either from an insufficient decrease of the angle of attack, or by not allowing the aircraft to accelerate to flying speed before pulling up to regain lost height. To avoid or correct this situation, the solution is simply to maintain full or maximum power and relax any back pressure, or move the control column forward slightly, and allow the aircraft to regain a safe flying speed before regaining lost height. During airline type conversion training on large aircraft, full stalls are not practiced except in flight simulators. To familiarize pilots with the characteristics of their aircraft, only the approach to the stall, down to stick shaker activation, is carried out. For jet aircraft with swept wings, there are no special considerations during the approach to the stall. At the stick shaker, either power on or power off, the aircraft can be recovered by moving the control column smoothly forward until the shaker stops, simultaneously increasing power to the maximum recommended to minimize height loss, and preventing or correcting any wing drop with roll control and rudder to balance, then raising gear and flaps at appropriate speeds if down. For multiprop aircraft, the recovery sequence is almost identical, except that the wings should be levelled with coordinated use of rudder and aileron. The reason for this difference is that the propeller-driven aircraft will experience rapid changes in slipstream and propeller torque during the power increase, and it is essential that the pilot coordinates his control movement during the power change to keep the aircraft in balance. That is, with the ball in the middle. Prevention of yaw is particularly important during stall and recovery. For single-engine propeller aircraft, an incipient stall recovery at the stall warning involves moving the control column smoothly forward to unstall the wings, which is judged by the absence of the stall warner or any signs of an incipient stall, and, at the same time, increasing the power to maximum. Yaw should be prevented with rudder, and the wings levelled with aileron once unstalled, then height regained. A power on stall and recovery pose extra complications. At the nose high attitude associated with a power on stall, there will be appreciable turning effects from the propeller. These will be discussed in the lessons on propellers. Pilots of single-engine aircraft, when flying at low speeds, must be prepared to compensate for the effects of the propeller and of power changes in all three axes, and of gyroscopic forces from the propeller if the nose drops during a stall. It is worth reiterating that any tendency to yaw must be stopped to avoid a spin. This would be particularly true in a high-power, low-speed situation, such as after takeoff or during a go-around, where the pilot's attention could be diverted from the speed and balance. If a stall does occur in this situation, correct and immediate recovery action should be taken at the first sign. Forward movement of the control column, ailerons neutral, and rudder to prevent yaw. A stall that develops into a spin at low level could be irrecoverable. When an aircraft is in a level coordinated turn at a constant angle of bank, the inside wing is moving through the air at a slightly lower speed than the outside wing, and consequently generates less lift. If the ailerons are exactly neutral, the aircraft would have a tendency to roll in the direction of bank, or over bank. If the pilot holds the required attitude and bank angle, he will actually be holding a small aileron deflection to oppose the roll, sometimes known as holding off bank. The deflection, although probably undetectable from control column position, is greater for low speeds than for high speeds. The inner or lower wing will have a slightly greater angle of attack than the outer wing because of the difference in aileron position, and may reach the critical angle first. In a climbing turn, the airspeed is likely to be lower, but with full or high power, and in a single propeller aircraft, the rolling and yawing forces from the propeller and its slipstream will add to the control deflections required for balanced flight, and may complicate the aircraft's reactions in a stall. In a descending turn, the power is likely to be at a low or idle setting. In the event of a stall, the pilot would need to counteract the forces arising around all three axes as the power is increased through most or all of its range during a stall recovery. As with any situation, it is important for the controls to be coordinated, and particularly so where the aircraft is at or close to the stall, to prevent an inadvertent spin. Regardless of configuration, attitude, speed or power setting, the correct action to be taken by the pilot in the event of a stall warning is to carry out the stall recovery technique applicable to the type of aircraft. Invariably, this will include decreasing the angle of attack below the critical angle to unstall the wings, simultaneously applying maximum permissible power to accelerate and minimize height loss and prevent yaw from developing. At any stage of flight, it is important to fly in balance. But when close to the stall, it is essential to keep control movements coordinated to avoid an inadvertent spin. Remember, keep the ball in the middle. When explaining the basic principles of flight, we consider air to be incompressible at speeds less than 4/10 of the speed of sound, or Mach 0.4. Or, in other words, that pressure is considered to have no effect on air density. At speeds above Mach 0.4, which is about 300 miles per hour, it is no longer practical to make that assumption, because density changes in the airflow around the aircraft begin to affect the behavior of the aircraft. At high altitude, a large high-speed jet transport will be cruising at a speed marginally above its critical Mach number, and will have a small shock wave on the wing. If the aircraft's speed is increased, the shock wave will rapidly grow larger, causing the static pressure to increase sharply in the vicinity of the shock wave. The locally increased adverse pressure gradient will cause the boundary layer to separate immediately behind the shock wave. This is called a shock stall. The separated airflow will engulf the tailplane in a very turbulent wake, which will cause severe airframe buffeting, obviously an undesirable phenomenon. This high-speed buffet, or shock stall, can seriously damage the aircraft structure. So an artificial warning device is installed to alert the flight deck crew if the aircraft exceeds its operational speed limit by even a small amount. The limits are VMO, the maximum operating indicated airspeed, and the equivalent Mach number, MMO. The high-speed warning is oral, either a clacker, horn, or siren, and is designed to be easily distinguishable from the low-speed stick shaker triggered by high angle of attack. The warning will not be cancelled until the speed is reduced below the speed at which it is triggered. You have learned that approaching the critical angle of attack can cause airframe buffeting, low-speed buffet. And we have now shown that flying too fast can also cause buffet, high-speed buffet. Any airframe buffet is undesirable, and, if allowed to become prolonged, can lead to structural damage, as well as upsetting the passengers. At high cruising levels, around 36 to 42,000 feet, the margin between the normal stall warning stick shaker and the high-speed warning may be as little as 15 knots. High speeds are operationally necessary, and designers are constantly trying to find ways of increasing maximum speeds without incurring any undesirable flight characteristics. The limits mentioned just now, VMO and MMO, are investigated and established during certification flight testing of new types. These maxima give a speed margin into which an aircraft can momentarily overspeed and be recovered by the pilot before any undesirable effects occur. This lesson concludes the series on stalling. The problems incurred by shock stall, such as tuck, loss of control effectiveness and instability, are covered in detail in the lessons on high-speed flight. Aircraft are fitted with flaps to reduce the takeoff and landing run. The reduction in takeoff and landing run is achieved by reducing the minimum operating speed. The minimum operating speed typically provides a 30% margin of safety above stall speed. Here you can see the transpose lift formula you were introduced to in previous lessons. Please note the typical stall speed for a jet transport aircraft of 131 knots, indicated airspeed, and the associated minimum operating speed that is 30% higher. You can see that increasing the maximum lift coefficient, CLmax, gives a decrease in stall speed, and therefore a decrease in minimum operating speed. CLmax is increased by temporarily increasing the camber of the wing with flaps. Only trailing edge flaps are illustrated for the moment. Flaps are a hinged portion of the trailing or leading edge of the wing that can be deflected downwards and so produce an increase in camber. For low-speed aircraft, the flaps will be on the trailing edge only, but on high-speed jet transport aircraft, there will be flaps on the trailing edge and the leading edge. We will consider the common types of trailing edge flap first. The plane flap is usually fitted to light aircraft and is of simple construction. The plane flap gives a good increase in CLmax, but with fairly high drag. Here we show a 10-degree flap selection. 10 degrees of flap will be ideal for takeoff, because CLmax will be increased a moderate amount, but drag will increase only slightly. Prior to landing, flaps should be selected in small increments, and 10 degrees would be the initial selection. It should be noted that any amount of flap will increase drag. The significance of this fact will be explained later. Further flap selection will continue to increase CLmax. Selecting flap angles of 20, 30 or 40 degrees will continue to increase CLmax, but also give a significant increase in drag. So the larger angles are usually used for the approach to landing, when the extra drag is an advantage. The next type of trailing edge flap we'll consider is the split flap. The difference from the plane flap is that the split flap only moves the lower surface of the trailing edge. The next type of trailing edge flap we'll consider is the slotted flap. When the slotted flap is lowered, a slot is opened between the leading edge of the flap and the trailing edge of the wing. The slot directs high-energy airflow from the bottom surface of the wing onto the upper surface of the flap. This increases the kinetic energy in the boundary layer over the flap. Therefore, the slotted flap can be lowered to a larger angle before airflow separation begins. This allows a greater increase in CLmax with much less drag than is possible with either the plane or the split flap. A slotted flap can have more than one slot. Double or triple slotted flaps are usually fitted to larger aircraft, which can offset the higher weight and greater complexity against the increased efficiency. The most efficient type of trailing edge flap is the Fowler flap. Fowler flaps are fitted to both large and small jet transport aircraft. When flaps 1 is selected, the first movement is rearward, which increases the wing area. You can see that increasing the wing area also decreases the stall speed and the minimum operating speed. Flaps 1 is useful for loitering in the terminal area, because there is a useful reduction in stall speed, but no significant increase in drag. When selections greater than flaps 1 are made, the camber starts to increase. Flaps 5 or flaps 15 are typical selections for takeoff. As before, the larger flap settings are used for the approach to landing. We will now select flaps up. This is a non-practical selection and speed of operation. If you selected flaps all the way up like this when flying, the aircraft would sing like a stone. We are resetting the scene to consider slotted Fowler flaps. For maximum efficiency, Fowler flaps can have as many as 3 slots. This example shows triple slotted Fowler flaps as fitted to large jet transport aircraft, such as the Boeing 747. Again, this animation is not practical. We are merely showing the type of flap. You can see here the effect of the type of flap on CL max. The plain flap and the split flap have nearly the same ability to increase CL max. The slotted flap benefits from the greater angle to which it can be deployed without suffering airflow separation. But the best type of flap for increasing CL max is the Fowler flap. We now need to highlight the difference between the change in lift coefficient and the change in drag coefficient with increasing flap angle. In this example, we have selected flaps 5. You can see that the increase in lift coefficient is much greater than the increase in drag coefficient. With a selection from flaps 5 to flaps 10, you can see the increase in lift coefficient is less, while the increase in drag coefficient is greater. As the flap angle is increased, there will be a progressively smaller increase in lift coefficient and a larger increase in drag coefficient. This is the reason why the larger selections of flap are reserved for the landing approach, when a large amount of drag is a benefit. For takeoff, only the smaller flap angles are used, because drag must be kept to a minimum to optimize aircraft acceleration. This will be discussed in more detail in later lessons. The CL angle of attack graph shows a reduced stall angle with trailing edge flaps selected. This is because the lift curve is plotted using the original chord line, before the flaps are lowered. When the pilot lowers the trailing edge flaps, the wing camber is increased, and if the pilot did not prevent it, lift would increase. As the flaps deploy, the pilot must reduce the angle of attack so that the effective angle of attack remains constant and that lift still equals weight. Please remember that any amount of flap will increase drag. We have already seen that CL max increases as the flaps are lowered, but unfortunately drag will also increase, so we need to consider LD max. We must generate enough lift to balance the weight, but at the same time, drag must be a minimum. Therefore, drag will divide into lift the maximum number of times. We call that LD max. The following illustrations will show the efficiency of flaps. The greater the LD max, the greater the aerodynamic efficiency. If a tangent is drawn from the origin of the graph to the curve of the lift-drag polar plot, the angle between the straight line and the horizontal axis is a measure of LD max. We will now compare the aerodynamic efficiency of the previously mentioned types of flap with that of no flap. Here you can see the CL-CD polar of the plane flap. Notice that the angle between the straight line from the origin and the horizontal axis is less than that for no flap. This shows a decrease in LD max, which is a reduction in aerodynamic efficiency. This is the CL-CD polar of the split flap, together with the plane flap. Notice the angle between the split flap straight line from the origin and the horizontal axis is again less than that for no flap, but pretty much the same as the plane flap. Therefore, the plane and the split flap have approximately the same aerodynamic efficiency. Now you can see the slotted flap polar. Less drag is generated, and it is more aerodynamically efficient than either the plane or the split flap. But again, LD max is less than with no flap. Here, we see the most aerodynamically efficient type of trailing edge flap, the Fowler flap. But once again, it has a lower LD max than no flap. Does an understanding of reduced LD max with flaps down have a practical application? Yes, it is a very important takeoff climb consideration. We have learned that the use of about 15 degrees of flap reduces the takeoff run. That's why flaps are fitted. But any amount of flap reduces the ability to climb. We can see that takeoff flap reduces the takeoff run required, but also reduces the ability of the aircraft to climb. When carrying out aircraft performance calculations prior to flight, this conflict must always be considered. Depending on the length of runway available and any obstacles present during the initial climb, it might be better to use no flaps for takeoff. This will be explained in more detail in future lessons. Flap movement, both up and down, may generate an aircraft pitching moment. Any pitching moment generated is due to movement of the centre of pressure, CP, and changes in downwash. Note that the CP is aft of the aircraft, CG. This generates a nose-down pitching moment. The aircraft, however, is in equilibrium because of the matching nose-up pitching moment from the downforce on the tail. First, we will consider movement of the CP. Only the top surface pressure distribution will be shown. As the flaps deploy, there is a general increase of suction on the top surface, but there is also an increased acceleration of the airflow in the vicinity of the flap hinge. This produces a localized reduction in pressure, which moves the CP aft, and an aircraft nose-down pitching moment is generated. Let us now take a look at the effect of downwash. You can see that as the flaps deploy, the downwash increases. This increases the downforce on the tail and generates an aircraft nose-up pitching moment. It is now obvious that flap deployment generates two pitching moments, a nose-down pitching moment from the wing and a nose-up pitching moment from the tail. So, if you are asked the question, what pitching moment does the aircraft experience when trailing edge flaps are deployed? The only answer you can give is, it depends. The net pitching moment the aircraft experiences will depend upon which of the two pitching moments is dominant. On some aircraft, the net pitching moment will be nose down. On some aircraft, the net pitching moment will be nose up, and on other aircraft, there will be no net pitching moment. However, if the aircraft you are flying has fouler flaps, it will usually generate a net nose-down pitching moment when the flaps are deployed. Because fouler flaps increase the wing area by moving rearwards when deploying, a larger nose-down pitching moment is generated. This gives an increased tendency to generate a net aircraft nose-down pitching moment when the flaps are lowered. If a T-tail is fitted to an aircraft, it will also influence the net aircraft pitching moment. A T-tail is attached in a higher position, so the change in downwash from flap deployment will have a smaller influence on the tail force, and a reduced nose-up pitching moment is generated. This animation repeats the fact that as flaps are lowered, the pilot must decrease the angle of attack, so that lift remains the same as the weight. Therefore, with flaps down, the aircraft will fly in a more nose-down attitude. On approach to landing, this is an advantage, as it gives a better view of the runway. Because of the high minimum speed of jet transport aircraft, even the fitment of trailing edge flaps does not reduce the takeoff and landing run to acceptable values. For this reason, in addition to the most efficient trailing edge flaps, jet transport aircraft must also be fitted with leading edge flaps. The next lesson will examine leading edge flaps in detail, plus the operational details of high lift devices. The design of jet transport aircraft is biased towards maximum efficiency at high speed. Unfortunately, they will also have a high minimum operating speed, and even the most efficient trailing edge flaps will not reduce the takeoff and landing run to acceptable values. Therefore, jet transport aircraft must also be fitted with leading-edge high-lift devices, known as flaps or slats. This lesson will examine the three main types of leading-edge high-lift device in detail, in their order of increasing efficiency. Being the least efficient, we will begin with the Kruger flap. The illustration shows a cross-section through the leading edge of the wing. You can see that the Kruger flap forms part of the leading edge lower surface. When fully out, the Kruger flap gives a smoother path for the airflow over the leading edge of the wing, allowing the airflow to retain maximum kinetic energy. Kruger flaps are either in or out. There are no intermediate angles like trailing edge flaps. Operationally, leading edge devices are usually used together with the trailing edge flaps. But for reasons of clarity, only leading edge devices will be illustrated. There is usually only one flap lever on the flight deck. When the flight crew makes a flap selection, an aircraft system will schedule the leading edge devices to operate in conjunction with the trailing edge flaps at the appropriate time. In this example, a selection of flaps 1 activates the Kruger flaps. They will remain fully out until the flaps are selected from flaps 1 to flaps up during retraction. With the Kruger flaps out, the camber of the wing is increased. And as you can see, CL max is increased. In addition, the forward end of the chord line is lowered, which increases the stall angle. The next type of leading edge device to consider is the variable camber leading edge flap. The variable camber is more efficient than the Kruger flap. The reason for its increased efficiency is that the variable camber leading edge flap has a mechanism that curves the flap surface as it extends. When fully out, the variable camber flap gives an even smoother path for the airflow than the Kruger flap, allowing maximum retention of kinetic energy in the boundary layer. Again, there are no intermediate selections possible. They are either in or out. In practice, their speed of operation is about twice that illustrated. With the variable camber leading edge flaps out, the camber of the wing is increased slightly more than with the Kruger flap. And as you can see, CL max is also increased. The forward end of the chord line is once again lowered, which increases the stall angle. Now we come to the most efficient leading edge high lift device, the slat. To illustrate the effect of slats, a wing is shown at a high angle of attack, with the airflow just starting to separate at the trailing edge. The aircraft is positioned on the lift curve. As the slats are driven open, high-energy air from under the leading edge flows onto the top surface of the wing. This increases the kinetic energy in the boundary layer, which in this example reattaches the airflow. Slats increase CL max by increasing the boundary layer kinetic energy. This merely extends the lift curve. If a constant angle of attack is maintained, the lift coefficient of the aircraft will remain the same, and there will be no operational change. For the aircraft to benefit from slats, the pilot must fly the aircraft at a higher angle of attack, a higher nose attitude. There are two disadvantages with the higher nose attitude. Firstly, when rotating the aircraft for takeoff or flaring to land, there is an increased tendency to tail strike. Secondly, there is reduced visibility from the flight deck when approaching to land. Here, we can see a sketch of the low pressure area on the top of the wing, with the aircraft at a high angle of attack. Suction is reduced towards the trailing edge because of minor airflow separation. When slats are driven open, we know that the increased boundary layer kinetic energy reattaches the airflow. The low pressure area becomes more evenly distributed, but the total area changes very little. Please note that the suction peak does not move forward, so the effect of slats on aircraft pitching moment is insignificant. Some jet transport aircraft have an automatic system that will fully extend the slats for stall protection. If the aircraft approaches the stall angle too closely, the automatic slat system will extend the slats to the fully open position. This illustration shows the order of increasing stall angle for flaps. The configuration that gives the lowest stall angle is trailing edge flaps. The next higher stall angle is no flaps, and the highest stall angle is leading edge flaps. This is not an operational consideration, but the examiners might ask you. If a flap selection is made, and, due to a fault of some kind, only the flaps on one side move, the rolling moment generated can be greater than the pilot can oppose with roll control. Flap asymmetry must be prevented. To avoid the possibility of flap asymmetry, transport aircraft are usually fitted with a flap asymmetry protection system. Devices monitor flap extension angles on each half of the wing, and if an asymmetry of greater than 1 or 2 degrees is detected, the mechanism that drives the flaps is switched off, and a warning on the flight deck will alert the pilots. Transport aircraft can be fitted with a flap load relief system, which prevents the flaps deploying if the indicated airspeed is too high. The pilot can move the flap selector, but the flaps will not extend until the indicated airspeed is reduced to the value appropriate for that flap setting. These flap angle limiting indicated airspeeds are known as VFE. Excessive dynamic pressure can damage the flaps themselves, their hinges and operating systems, or the wing. In this example, flaps 25 has been selected at too high an indicated airspeed. In other words, above VFE for flaps 25. The flap load relief system prevents the flaps from moving. The aircraft is now slowed to VFE for flaps 25, and the flaps move down to 25 degrees. The indicated airspeed is now reduced to VFE for flaps 30. When flaps 30 is selected, the flaps move down to 30 degrees. But if the indicated airspeed is allowed to increase, the flap load relief system will drive the flaps back to flaps 25. If now the indicated airspeed is reduced to VFE for flaps 30, the flaps will move down to 30 degrees of flap again. Here, we will only consider the effect of flaps on the takeoff and landing run. Other variables will be covered in future lessons. We will consider takeoff flaps first. The length of the takeoff run is affected by the minimum indicated airspeed at which the aircraft can safely fly. But the length of the takeoff run is also affected by the rate of acceleration. The minimum safe takeoff speed will be possible at the highest CL max, and this will be achieved at the largest flap setting. But large flap angles also generate the most drag, which will decrease aircraft acceleration and make the takeoff run longer. A smaller flap angle will give less CL max, which will result in a higher takeoff speed, but the reduction in drag will give better acceleration. Taking both CL max and drag into consideration, there will be an optimum flap angle that will give the shortest possible takeoff run. For jet transport aircraft, the optimum flap angle for takeoff is approximately 15 degrees. We can see that increasing flap angles result in a decreasing takeoff run. But beyond the optimum takeoff flap angle, the distance increases. What is the point in not using all of the runway length that is available? The operational advantage of using the optimum flap angle for takeoff is to carry more weight from a given runway length. After takeoff, a minimum climb gradient is required. The ability of an aircraft to climb is reduced by flaps because of the extra drag they generate. So, if the required minimum climb gradient will limit the maximum takeoff weight, a smaller flap angle will be used for takeoff, even though it will result in a longer takeoff run. If runway length is not limiting, you can see that the maximum takeoff climb limited weight will be achieved with no flaps. To reduce the landing distance, maximum flap angle should normally be used. This results in a lower minimum speed because of the high CL max, and a steeper approach path and increased deceleration because of the high drag. This aircraft has just taken off, and it is now time to retract the flaps. Note the indicated airspeed of 150 knots and the aircraft position on the flaps down lift curve. As the flaps retract, the lift coefficient decreases. Lift is now less than the weight, and the aircraft will sink. Increasing the angle of attack to keep lift the same is not an option, because as you can see from the lift curve, the aircraft will stall. Obviously, this is not the way to retract the flaps. We must trade indicated airspeed and angle of attack to keep lift the same as the weight. Let's reset the original conditions to consider the correct way to retract the flaps after takeoff. Before retracting the flaps, the indicated airspeed must be increased to VZF, the minimum indicated airspeed for zero flap. As the indicated airspeed increases, the angle of attack must be decreased to keep lift constant. Now when the flaps are retracted, the pilot can increase the angle of attack to keep the lift constant. When considering flap extension prior to landing, we can use the same principle of trading indicated airspeed and angle of attack to keep lift the same as the weight. As the flaps extend, the pilot must decrease the angle of attack. Just in case the examiners ask you, please note that to maintain level flight at a constant indicated airspeed as the flaps extend, the lift coefficient must remain constant. With the aircraft now on the flaps down lift curve, the pilot can decrease the indicated airspeed while increasing the angle of attack to keep lift the same as the weight. The fore and aft position of the centre of gravity will have a significant effect on longitudinal static stability. The illustration shows a centre of gravity position at which the stabilising tail moment is bigger than the destabilising wing moment. The aircraft will have some measure of longitudinal static stability. If the centre of gravity moves forward, the length of both arms change. The tail arm becomes longer, which makes the stabilising moment bigger. And at the same time, the wing arm becomes shorter, which makes the destabilising moment smaller. Therefore, with the centre of gravity in a more forward position, the aircraft has more longitudinal static stability. If the centre of gravity moves aft, the length of both arms will change again. The tail arm becomes shorter, which makes the stabilising moment smaller. And at the same time, the wing arm becomes longer, which makes the destabilising moment bigger. Therefore, with the centre of gravity in a more aft position, the aircraft has less longitudinal static stability. Now let's consider what would happen if the centre of gravity is moved further aft. A CG position would eventually be reached when both the destabilising moment and the stabilising moment are the same. If a gust were to change the angle of attack, the aircraft would be displaced from equilibrium, but no net pitching moment would be generated. The aircraft would not displace any further, but would not start to return towards its previous equilibrium either. It would stay displaced. What type of longitudinal static stability would this be? Neutral longitudinal static stability. The CG position that will give the aircraft neutral longitudinal static stability is called the neutral point. Operationally, you would never fly an aircraft with the CG on the neutral point. You might think that neutral longitudinal static stability is not too bad. But remember, the aircraft must always be flown with a margin of safety. If the CG were to move after the neutral point, the aircraft would have negative longitudinal static stability, and when hit by a gust, will continue to displace from equilibrium, which is obviously not acceptable. Having returned the CG to the neutral point, we will now consider the acceptable CG range. If we move the CG slightly forward of the neutral point, the aircraft would have a small amount of longitudinal static stability, but there would still be an insufficient margin of safety. Moving the CG slightly further forward will increase longitudinal static stability a little more, but will still not provide a big enough margin of safety. With further forward movement, eventually a CG position will be reached when the minimum acceptable longitudinal static stability exists. The CG position that guarantees minimum acceptable longitudinal static stability is known as the aft CG limit. Operationally, the CG must never move outside the aft CG limit at any time during the flight. Calculating the CG position during the entire flight will be fully covered in a different subject called mass and balance. If we now move the CG forwards of the aft CG limit, the longitudinal static stability will increase. But we don't want the CG too far forward, because there is such a thing as too much longitudinal static stability. You might think the more longitudinal static stability, the better. But no. In addition to our example gust, the pilot can also momentarily change the angle of attack when a pitch input is made. Longitudinal static stability will oppose the pilot's pitch input in the same way it opposes a gust. The greater the stability, the more the resistance to pitch input. So, in addition to the effect of CG position on longitudinal static stability, we must also consider the effect of CG position on the ability of the pilot to maneuver the aircraft in pitch, and the stick forces required. Consequently, to ensure minimum ability for the pilot to maneuver the aircraft in pitch, plus ensure the stick forces are not too high, a forward CG limit is required. The forward CG limit will give maximum longitudinal static stability and guarantees minimum acceptable maneuverability and maximum acceptable stick forces. The aft CG limit will give minimum acceptable longitudinal static stability and gives maximum maneuverability and minimum acceptable stick forces. We will now take what we have learned about longitudinal static stability and, using simple sketch graphs, consider some of the variables. Here are the two axes. The vertical axis represents pitching moment, with increasing nose-up pitching moment above the horizontal axis and increasing nose-down pitching moment below. The horizontal axis represents lift coefficient, increasing to the right. Your previous knowledge will tell you that the horizontal axis could instead be labelled angle of attack or decreasing indicated airspeed. As you will see, all three values need to be considered to give a full understanding of these graphs. For the time being, we will use lift coefficient for the horizontal axis, but you need to keep the two alternative values in mind. An aeroplane in equilibrium is shown on the horizontal axis. How do we know it's in equilibrium? Because it is not generating a nose-up pitching moment or a nose-down pitching moment. An upward acting gust has increased the lift coefficient. and because the aircraft has some longitudinal static stability, it will generate a nose-down pitching moment. The nose-down pitching moment will start the aircraft back towards equilibrium. Remember, longitudinal static stability is just the initial reaction to a change in angle of attack. The graph is reset with the aircraft in equilibrium. A downward acting gust now decreases the lift coefficient. Because of its longitudinal static stability, the aircraft will once again generate a pitching moment, but this time it's a nose-up pitching moment. The nose-up pitching moment will start the aircraft back towards equilibrium. The graph is again reset with the aircraft in equilibrium. If we join together the point on the graph that represents the aircraft in equilibrium, the point that represents the pitching moment generated by an increase in angle of attack, and the point that represents the pitching moment generated by a decrease in angle of attack, the plot will represent a longitudinally statically stable aircraft. The curve on the right-hand end of the plot shows the aircraft nose-down pitching moment at the stall. Now let's use the graph to consider variations in longitudinal static stability. Movement of the red dot shows an increase in angle of attack, which generates a nose-down pitching moment. Reset the graph to equilibrium. A decrease in angle of attack generates a nose-up pitching moment. Now we'll look at a decreased level of longitudinal static stability. The same increase in angle of attack has generated a smaller nose-down pitching moment. Reset the graph to equilibrium. The same decrease in angle of attack has also generated a smaller pitching moment, but this time nose up. Now we'll look at an increased level of longitudinal static stability. The same increase in angle of attack has generated a much bigger nose-down pitching moment. Reset the graph to equilibrium. The same decrease in angle of attack has also generated a much bigger pitching moment, but this time nose up. The green plot shows longitudinal static stability. The blue plot shows less longitudinal static stability. The magenta plot shows more longitudinal static stability. The direction of all three plots is downward, from left to right. This indicates positive longitudinal static stability. The angles of the plots shows the amount of longitudinal static stability. The steeper the plot, the greater the stability. What does this plot represent? An increase in angle of attack generates no pitching moment, nor does a decrease in angle of attack. This plot represents neutral longitudinal static stability. What do you make of this plot? An increase in angle of attack generates a nose-up pitching moment. This is not good. Reset the graph. A decrease in angle of attack generates a nose-down pitching moment. Again, this is not good. When the slope of the plot is upwards, from left to right, it represents negative longitudinal static stability. As with positive longitudinal static stability, the steeper the slope, the greater the instability. Here are the three types of plot we'll be using from now on: stable, neutral, and unstable. So what does this plot represent? Here's a big clue. The plot represents an aircraft with a swept wing. Stable at high speed because the plot slopes downward to the right. The plot continues to slope downward to the right as speed is reduced. But the slope is becoming less steep, which represents a slight decrease in longitudinal static stability. With further reduction in indicated airspeed, the stability becomes neutral. From your previous studies of swept wing stall at higher angles of attack, tip stall will begin. And like all swept wing aircraft, this will generate a nose-up pitching moment. In the next segment, we will be using graphs like these to illustrate other variables. The net pitching moment about the lateral axis is due to the contribution of each of the component surfaces. A fact the examiners might be interested in is that the wing camber has no effect on longitudinal static stability. This is because the pitching moment about the aerodynamic centre is always nose down, regardless of angle of attack. The contribution of the wing has already been explained in previous lessons. But to remind you, the wing is destabilizing because the aerodynamic centre is forward of the aircraft CG. At the small angle of attack used in the cruise, the fuselage acts as a symmetrical aerofoil. The reduction in pressure on the top is the same as the reduction in pressure on the bottom, with an area of stagnation pressure at the nose. Under these conditions, the fuselage generates no pitching moment. Any change in angle of attack generates an aircraft pitching moment, which is destabilizing. The pitching moment is generated by the change in pressure distribution on the fuselage and nacelles. As we have already established, the tailplane is the aerofoil that provides the stabilizing influence to the aircraft. This is due to the stabilizing pitching moment it generates when the aircraft is subjected to a change in angle of attack. For simplicity, the first explanation of longitudinal static stability assumed a gust would give the same change in angle of attack to the tailplane and the wing. In practice, the airflow at the tailplane will be affected by the airflow from the wing trailing edge, as illustrated, and the tailplane will experience a smaller change in angle of attack than the wing. The designers ensure the tailplane can always generate the appropriate stabilizing moment by attaching the tailplane at a smaller angle of incidence than the wing. This is called longitudinal dihedral. The illustration shows a wing incidence of 4 degrees and a tailplane incidence of 2 degrees. If a gust of wind increases the angle of attack by 4 degrees, the change in wing lift will be 100%, whereas the change in tailplane lift will be 200%. The graph shows a typical build-up of components and their effect on longitudinal static stability. The wing is destabilizing. The wing and the fuselage together are even more destabilizing. The tailplane contribution is very stabilizing. And when we consider everything together, the aeroplane has the required degree of longitudinal static stability. Notice the location of the CG in the illustration is listed as 20% MAC. The mean aerodynamic chord is used as a reference point from which the location of the CG is measured as a percentage. The higher the percentage, the further aft the CG. We can use the graph to show the effect of CG position on longitudinal static stability. With the CG at 10% MAC, the aircraft is stable. The aircraft is less stable with the CG at 20%. and even less stable with the CG at 30%. 40% MAC is the neutral point. And with the CG at 50% MAC, the aircraft will be unstable. The neutral point and 50% MAC are shown with a dashed line, because operationally the CG must never be positioned outside the aft CG limit. The effect of thrust on longitudinal static stability will be greatest at low indicated airspeed and high thrust, such as during takeoff and the approach to landing. The vertical location of the thrust line defines one of the contributions. The illustration shows an aircraft with pod-mounted engines beneath the wing. Because the thrust line is below the aircraft CG, an increase in thrust will produce a nose-up pitching moment, which is destabilizing. A propeller located forward of the CG will also contribute a destabilizing effect. The change in momentum of the prop wash will generate a force normal to the plane of the propeller. It has already been stated that a stable aeroplane will resist displacement from equilibrium. The control surface displacement and the control forces should reflect the stability of the aeroplane and provide suitable reference to the pilot for precise control of the aeroplane. The effect of elevator deflection on pitching moment is illustrated. The elevator is neutral to the tailplane, and the aircraft is flying level at a given lift coefficient. A momentary increase in angle of attack generates a stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates a stabilizing nose-up pitching moment. Reset the graph. The illustration shows a certain amount of static longitudinal stability, with the elevator at neutral. The aircraft is maintaining level flight by increasing the angle of attack as the indicated airspeed is decreased, until once again it is in equilibrium at a lower airspeed. To hold this angle of attack at a lower airspeed, the elevator must remain displaced at a position 10 degrees up from neutral. A momentary increase in angle of attack generates the same stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates the same stabilizing nose-up pitching moment. Reset the graph. The illustration has shown the same amount of static longitudinal stability with the elevator at 10 degrees up as it did with the elevator neutral. This is easily seen at a glance from the fact that the two plots are parallel. Now the aircraft is continuing to maintain level flight by decreasing the angle of attack as the indicated airspeed is increased, until once again it is in equilibrium at a higher airspeed. To hold this angle of attack at a higher airspeed, the elevator must remain displaced at a position 10 degrees down from neutral. A momentary increase in angle of attack generates the same stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates the same stabilizing nose-up pitching moment. Reset the graph. The illustration has shown that the same amount of static longitudinal stability will be obtained with the elevator at 10 degrees down, neutral, and 10 degrees up. Elevator position does not affect longitudinal static stability because only the change in lift is considered. We can now consider the effect of CG position on elevator deflection. Please note that the vertical axis of the graph now represents elevator deflection. With the CG at 10% MAC, the aircraft will have a lot of longitudinal static stability, and a large up elevator deflection is required to maintain a given lift coefficient. With the CG further aft at 20% MAC, there is less longitudinal static stability, and less up elevator is required to hold the same lift coefficient. With the CG even further aft at 30% MAC, there is less longitudinal static stability, and less up elevator is required to hold the same lift coefficient. This animation illustrates the increase in aircraft controllability with an aft CG. Please note that the horizontal axis of the graph now represents indicated airspeed. All aircraft must have something called stick position stability. This means that the aeroplane must require the stick to be moved aft to increase the angle of attack, and trim at a lower indicated airspeed, and to be moved forward to decrease the angle of attack and trim at a higher indicated airspeed. While maintaining level flight, as the indicated airspeed is reduced, the elevator must be moved up. This requires the pitch control in the cockpit to be moved aft. Reset the graph. While maintaining level flight, as the indicated airspeed is increased, the elevator must be moved down. This requires the pitch control in the cockpit to be moved forward. Please note that the vertical axis now represents stick force. In addition to stick position stability, all aircraft must have stick force stability. This means that a push force must be required when indicated airspeed is increased, and a pull force must be required when indicated airspeed is decreased. The plot shows the stick force gradient with the aircraft in trim at low indicated airspeed. To maintain a reduced indicated airspeed of, let's say, 10 knots at low speed, a certain pull force is required. The plot now includes a stick force gradient with the aircraft in trim at a higher speed. To maintain the same 10 knot speed reduction from trim speed at a higher speed, a pull force is still required, but the required pull force is smaller. We can now consider the effect of CG position on stick force. From our previous studies, we know that moving the CG forward increases longitudinal static stability. With the CG at 30% MAC, a speed reduction requires a small pull force. With the CG at 20% MAC, the same speed reduction requires a larger pull force. With the CG at 10% MAC, the same speed reduction requires an even larger pull force. Moving the CG aft decreases the stick forces required to displace the aircraft from trim speed. Aerodynamic damping was first discussed when you were studying drag. We will now see how it can affect static stability. While the pilot is pitching the aircraft, the change in tailplane angle of attack is greater than the change in angle of attack of the wing because the tailplane is moving down. As soon as the pitch angle stops changing, the tailplane and the wing have effectively the same angle of attack. For the study of maneuver stability, we need to consider the period during the change in angle of attack. Study the vector diagram. It shows the tailplane with the true airspeed vector and the speed of tailplane down travel vector. The effective airflow direction is the resultant of the aircraft true airspeed and the speed of tailplane down travel while pitching. You can now see the increase in angle of attack while pitching, which generates an upforce that we know is aerodynamic damping. Aerodynamic damping gives a change in tail force, in this case upwards, while the pilot is pitching the aircraft nose up. At higher altitude, at the same indicated airspeed, the true airspeed is faster, which reduces the change in tail force for the same rate of aircraft pitch change. Let's consider the diagram we used earlier to define the neutral point. The neutral point is the position at which the CG would need to be for the destabilizing wing moment and the stabilizing tailplane moment to be the same. If we now add the change in tail lift to the change in tailplane lift due to a gust, the CG would have to be further aft for the wing moment and the tailplane moment to balance. This CG position is called the maneuver point. The maneuver point will always be aft of the neutral point. If we now look again at the aft CG limit and a sample aircraft CG position, you can see that the aircraft will always have more maneuver stability than static stability. This is because the distance from the maneuver point to the aircraft CG is greater than the distance from the neutral point to the CG. We can now take what we have learned about maneuver stability and apply it to a study of stick force versus load factor. An aircraft with positive maneuver stability should give a steady increase in stick force with increase in load factor, or G. The stick force per G must be positive, but neither too high nor too low. If the stick force per G is too high, the aircraft will be difficult and tiring to fly. If the stick force per G is too low, the aircraft may be accidentally overstressed because of the light control forces. You may be asked to calculate stick force per G, so you need to remember that in level flight the aircraft is at 1 G, and a manoeuvre that gives a load factor of 2.5 is only a 1.5 G increase. The graph shows a typical stick force gradient. A load factor of 1.6 G requires a 10-pound pull force, and a load factor of 2 G requires a stick force of 18 pounds. These stick force values don't represent any particular aeroplane and are just sample values. Let's now consider the effect of various CG positions on the stick force gradient, starting with the CG at 30% MAC. With the CG further aft at 40% MAC, the stick force gradient is reduced, in that, for the same load factor, the stick force is reduced. With the CG forward at 10% MAC, the stick force gradient is increased. For the same load factor, the stick force is higher. We can now consider the effect of altitude on stick force per G. At higher altitude, the stick force gradient is reduced. This is due to reduced aerodynamic damping. In conclusion, the possibility exists that the forward CG limit could be set to prevent an excessive stick force gradient, and thereby an inability for the pilot to manoeuvre the aircraft adequately. As the CG moves aft, the stick force gradient decreases, and the lower limit of stick force gradient may be reached, and the pilot could be in danger of too readily being able to accidentally overstress the aircraft. Designers can modify the stick forces, if required, to give adequate manoeuvrability throughout the entire flight envelope. The first device that can be used to tailor the control forces is the downspring. The downspring is used to increase the airspeed stick force stability. The downspring consists of a preloaded spring attached to the control system that tends to rotate the elevator down. The effect is to contribute an increment of pull force independent of control deflection or airspeed. The second device used to tailor the control forces is the bob weight. The bob weight consists of an eccentric mass attached to the pitch control system. The bob weight mass is subjected to the same change in load factor as the aeroplane. Thus, the bob weight will provide an increment of stick force in direct proportion to the load factor applied. This will prevent the pilot applying too much G during manoeuvres. The more the pilot pulls back, the more resistance the bob weight adds to the control system. An aeroplane must have adequate controllability as well as adequate stability. As previously mentioned, an aeroplane with high longitudinal static stability will have great resistance to displacement from equilibrium. There are three conditions of flight that provide the critical requirements of longitudinal control power: manoeuvring, takeoff, and landing. Any one or a combination of these conditions can determine the position of the forward CG limit. We will look first at the manoeuvring control requirements. The aeroplane should have sufficient pitch control power to achieve the maximum usable lift coefficient during manoeuvres. The illustration shows that with the CG forward at 10% MAC, the maximum elevator deflection is not capable of trimming the aeroplane at CL max. But with the CG slightly further aft at 18% MAC, maximum elevator deflection is now capable of trimming the aeroplane at CL max. Now for a look at the takeoff control requirements. At takeoff, the aeroplane must have enough elevator control power to be rotated to the takeoff attitude. Anything that increases the nose-down pitching moment will increase the amount of elevator deflection required for the same pitch attitude. For example, if the CG is further forward, or the rolling resistance is increased by, for instance, runway contamination. Now we can look at landing control requirements. When flaring to land, enough elevator control power must be available to rotate the aircraft to the required nose-up attitude. Anything that increases the nose-down pitching moment will increase the amount of elevator deflection required for the same pitch attitude, such as idle thrust, full flap, forward CG, and the aircraft in ground effect. Each of the longitudinal control power requirements are critical for high longitudinal static stability. If the forward CG limit were accidentally exceeded, the aeroplane may encounter insufficient controllability in any of these conditions. To conclude our study of longitudinal static stability, it must be remembered that the forward CG limit is set by the minimum permissible controllability, and the aft CG limit is set by the minimum permissible stability. You must keep your aircraft CG within the forward and aft limits at all times during the flight. It is now time to look at dynamic stability. We can then apply what we learn to a study of longitudinal dynamic stability. We will first consider a type of dynamic stability called subsidence. This is not operationally possible for an aeroplane. The vertical axis is displacement from equilibrium, and the horizontal axis is time. The red dot represents an aeroplane in equilibrium. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start to move back towards equilibrium. This illustrates positive static stability. And over a period of time, the dot returns to equilibrium. This illustrates positive dynamic stability. Let's reset the graph and reintroduce the ball in the bowl. Displacement takes place. The disturbing force is removed, and an initial return towards equilibrium begins. Over a period of time, a return to equilibrium takes place. We have an illustration of positive static and positive dynamic stability. How is it possible for the ball to gently return to equilibrium with no oscillations? Damping. If the bowl is full of a viscous substance, such as syrup, the ball might act as illustrated. Now we will consider another type of dynamic stability, called divergence. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start to move further away from equilibrium. This illustrates negative static stability. And over a period of time, the dot continues to move away from equilibrium. This illustrates negative dynamic stability. We have a negative static and negative dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement away from equilibrium begins. Over a period of time, a further movement from equilibrium takes place. An illustration of negative static and negative dynamic stability. Let's have a look at neutral dynamic stability. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to stay displaced from equilibrium. This illustrates neutral static stability. And over a period of time, the dot continues to stay equally displaced from equilibrium. This illustrates neutral dynamic stability. We have neutral static and neutral dynamic stability. Another type of dynamic stability is called damped oscillation. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start back towards equilibrium. This illustrates positive static stability. And over a period of time, the dot continues to move back to equilibrium with several oscillations. This illustrates positive dynamic stability. We have positive static and positive dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement back towards equilibrium begins. Over a period of time, with several reducing oscillations through equilibrium, a return to equilibrium takes place. An illustration of positive static and positive dynamic stability. This is the ideal type of stability for an aeroplane, but in reality, it is not quite so good as illustrated. This next type of dynamic stability is called undamped oscillation. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start back towards equilibrium. This illustrates positive static stability. And over a period of time, the dot continues to oscillate through equilibrium with no reduction. This illustrates neutral dynamic stability. We have positive static and neutral dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement back towards equilibrium begins. Over a period of time, there is continuous oscillation through equilibrium, with no damping of motion. An illustration of positive static and neutral dynamic stability. Clearly, energy is being added for this to occur. The final type of dynamic stability is called divergent oscillation. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start back towards equilibrium. This illustrates positive static stability. But over a period of time, the dot continues to oscillate through equilibrium with an increase in displacement. This illustrates negative dynamic stability. We have positive static and negative dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement back towards equilibrium begins. But now, over a period of time, there is increasing oscillation through equilibrium. The only way this can occur is for energy to be added. The energy usually comes from the pilot trying to damp out the motion, but out of phase with it, making it worse instead of better. This is called pilot-induced oscillation. All aircraft must demonstrate the required amount of static and dynamic stability. If the aircraft were allowed to have static instability with a rapid rate of divergence, it would be very difficult, if not impossible, to fly. Longitudinal dynamic stability concerns the variation of displacement with time following a disturbance. Longitudinal dynamic stability consists of two basic types of oscillation: long-period oscillation, the phugoid, and short-period oscillation. We will consider the long-period oscillation, the phugoid, first. The phugoid is a gradual interchange of potential and kinetic energy about some equilibrium airspeed and altitude. The period of oscillation is between 1 and 2 minutes, so is easily controlled by the pilot. There are changes in altitude, attitude, and airspeed, but there is no significant change in angle of attack. Damping in the phugoid is weak. Short-period motion consists of rapid pitch oscillations, during which the aeroplane is constantly restored towards equilibrium by its static stability and the displacement being decreased by pitch damping. So flying at high altitude will tend to reduce dynamic stability due to the reduction in aerodynamic damping. Short-period oscillation involves rapid and significant changes in angle of attack, load factor, so can generate damaging flight loads to the aircraft structure. There is no significant change in altitude, attitude, or airspeed. The period of motion of 1 to 2 seconds is close to the normal pilot response lag time. There is the possibility that an attempt by the pilot to forcibly dampen oscillation may make it worse and produce instability. This concludes our study of longitudinal stability. We will consider directional stability and lateral stability next. Directional stability involves moments about the normal axis and their relationship with yaw or side-slip angle. A disturbing force has yawed the aircraft to the left. The angle between the relative airflow and the longitudinal axis is called the side-slip angle. This is a positive side-slip angle. If the aircraft is yawed to the right, it would be a negative side-slip angle. A question in the written exam might describe this aircraft as being nose to the left. However, a pilot would describe this aircraft as being in a right side-slip. If the aircraft illustrated has directional stability, when displaced from equilibrium, it would generate a stabilizing yawing moment to the right. The contribution of the fuselage is destabilizing because its aerodynamic center is forward of the aircraft CG. The side surface of the aircraft is referred to as the keel surface. There is an area of keel surface forward of the CG and an area of keel surface aft of the CG. For adequate directional stability, the keel surface aft of the CG must be increased with the addition of a fin, or as it's sometimes called, a vertical stabilizer. The fin generates a stabilizing moment that is larger than the destabilizing moment from the fuselage. You must appreciate that when taxiing, during the takeoff run and during the landing run, in fact, whenever the aircraft is moving with the wheels on the ground, the directional stability of the aircraft will always generate a yawing moment into the wind. This is known as weathercocking. The pilot must actively prevent weathercocking by use of the rudder. A swept wing also gives a small stabilizing moment. Whenever the aircraft side-slips, in this case to the right wing has a reduced sweep angle and the left wing has an increased sweep angle. This gives more lift on the right wing and less lift on the left wing. Consequently, the right wing has more induced drag and the left wing has less induced drag, which results in a small stabilizing contribution. We have seen that the fin gives an aircraft directional static stability, but sometimes a basic aircraft design undergoes modification to increase its fuselage capacity, which reduces its static directional stability. It is not possible to just fit a larger fin, so a device called a dorsal fin and/or a ventral fin can be added. These are both lightweight and simple to attach. The dorsal fin is more common, and not only increases the keel surface aft of the CG, but also decreases the aspect ratio of the fin. A high aspect ratio aerofoil has a certain stall angle, but a low aspect ratio has a larger stall angle. A swept-back aerofoil also has an increased stall angle. The majority of aircraft have a swept-back fin for this reason. Bear in mind that the side-slip angle of the aircraft is effectively an angle of attack, and if the fin were to stall, the aircraft would become directionally unstable. To review the makeup of directional static stability, we can see that the fuselage is destabilizing. The fin alone is very stabilizing, but has a limited maximum side-slip angle because of the possibility of fin stall. The complete aeroplane has directional static stability, which can be restricted by the stall angle of the fin. The addition of a dorsal fin can retain acceptable directional stability, and it reduces the likelihood of fin stall during normal operations. The final thing to consider is the purpose of the ventral fin. The illustration shows an aircraft flying at a small angle of attack, with a typical yawing moment to side-slip angle ratio. The plot shows an acceptable value of directional static stability. As the aircraft slows down, its angle of attack must be increased. The wake from the wing is now contacting the fin, and reduces its effectiveness. You can see the plot now represents the reduced level of directional static stability. The addition of a ventral fin will increase the directional static stability at high angles of attack. During this lesson, you may have noticed how directional static stability might interact with lateral static stability. Lateral static stability will be discussed next, and we can then investigate how directional and lateral stability interact with each other.